Imagine you are standing at the edge of a field, looking at a distant tree. You close your left eye, and the tree appears to be in one position against the horizon. Then you close your right eye instead, open your left, and the tree seems to jump slightly to the side. It has not moved. You have not moved. But the view has shifted because you are looking from two different points, the two eyes in your head, separated by a few centimeters. This is parallax. You have been using it your entire life without thinking about it. Your brain combines the two slightly different images from your two eyes and uses the difference to judge how far away things are. Close objects shift a lot when you switch eyes. Distant objects barely shift at all. Now imagine trying to do the same thing with a star. The star is so far away that the few centimeters between your eyes make no difference whatsoever. The shift is far too small to detect, so you need a bigger baseline. You need to look from 2 points that are much farther apart than your eyes. Fortunately, there is a way to do this. You just have to wait 6 months. In January, the Earth is on one side of its orbit around the Sun. In July, it is on the opposite side, roughly 300 million kilometers away from where it was in January. That is your baseline. Not a few centimeters, but the diameter of Earth's orbit. If you measure the position of a star in January and then measure it again in July, the star will appear to have shifted slightly against the background of more distant stars. The shift is tiny, but it is measurable. And from that shift you can calculate how far away the star is. This is stellar parallax. It is one of the oldest and most fundamental techniques in astronomy, and it is the reason the parsec exists. But here is the strange part. The parsec is not a convenient unit. It does not correspond to anything intuitive. It is not the distance light travels in some round number of years. It is not the radius of anything. It is not based on any natural phenomenon that humans experience directly. A parsec is the distance at which a star would appear to shift by exactly 1 arcsecond when viewed from opposite sides of Earth's orbit. An arcsecond is 1/60th of an arc-minute. An arc-minute is 1/60th of a degree. A degree is 1/360th of a full circle. So an arcsecond is an extraordinarily small angle. If you held up a coin at a distance of about 4 kilometers, it would appear to be roughly 1 arcsecond across. The parsec, then, is the distance at which that tiny shift, that 1 arcsecond wobble, would occur. Work out the geometry, and you get a distance of about 3.26 light-years, or about 31 trillion kilometers. This is a strange way to define a unit of distance. It is derived from an angle, from the geometry of triangles, from the specific size of Earth's orbit. It is convenient for astronomers doing parallax measurements because the math works out cleanly. If a star has a parallax of 1 arcsecond, it is 1 parsec away. If it has a parallax of half an arcsecond, it is 2 parsecs away. The relationship is simple. Distance in parsecs equals 1 divided by parallax in arcseconds. But for anyone not actively doing parallax calculations, the parsec is baffling. It has no everyday meaning. It does not connect to any experience a human being has ever had. And yet, astronomers continue to use it. Professional papers are filled with distances measured in parsecs. Catalogues of stars list their distances in parsecs. The scale of the universe, as far as working scientists are concerned, is denominated in this peculiar unit. Why? This is what we are going to explore. Not just what a parsec is, which is easy enough to explain, but why it persists. Why science, with all its precision and its advanced technology, still clings to a measurement unit invented in the 19th century for the purpose of making pencil and paper calculations easier. There is something gently absurd about this. We have sent robots to Mars. We have detected ripples in space-time from colliding black holes 1 billion light-years away. We have built machines that manipulate individual atoms. and we still measure the cosmos using a unit designed to simplify trigonometry for astronomers who calculated by hand. But the absurdity, once you understand it, becomes something else. It becomes a window into how science actually works. Not as a pristine march toward perfect knowledge, but as a human activity shaped by history, constrained by practicality, and surprisingly tolerant of imperfection. Let us start at the beginning. For most of human history, the stars were unreachable mysteries. People could see them, could track their motions across the sky, could group them into constellations and tell stories about them. But how far away they were remained unknown. There was no way to measure it. The idea that you could use parallax to measure stellar distances was old. Ancient Greek astronomers understood the principle. Aristotle knew that if the Earth moved around the Sun, as some philosophers proposed, then the stars should appear to shift position over the course of the year. He looked for this shift and did not find it. This led him to conclude, reasonably enough, that the Earth did not move. What Aristotle did not realize was that the stars were simply too far away. Their parallax was too small for the naked eye to detect. Even with the best instruments available for centuries afterward, no one could measure it. The shift was there, but it was hiding below the threshold of detection. This absence of detectable parallax was actually used as an argument against the heliocentric model. If the Earth orbited the Sun, critics said, we should see the stars shifting. We do not see them shifting. Therefore, the Earth does not orbit the Sun. Copernicus, who revived the heliocentric model in the 16th century, had an answer. The stars, he said, must be incredibly far away, so far that their parallax was simply too small to see. This was correct, but it must have seemed like a convenient excuse at the time. You cannot prove your theory, so you claim the evidence is just too small to detect. Skeptics were not impressed. For 3 centuries after Copernicus, astronomers tried to measure stellar parallax. They built better telescopes. They developed more precise instruments. They refined their techniques. And they failed. Year after year, decade after decade, no one could definitively measure the parallax of a single star. This was not for lack of trying. Some astronomers reported detections, but they turned out to be errors. The measurements were at the edge of what their instruments could achieve, and noise was mistaken for signal. The true parallax of even the nearest stars was smaller than the errors in the measurements. And then, in 1838, 3 astronomers independently succeeded. Friedrich Bessel in Germany measured the parallax of a star called 61 Cygni. Thomas Henderson in South Africa measured the parallax of Alpha Centauri. Friedrich Struve in Russia measured the parallax of Vega. Within a few years, the distances to these stars were known, at least approximately. The universe had suddenly become measurable. The parallax of 61 Cygni was about 0.31 arcseconds. This meant it was about 3.2 parsecs away, or roughly 10 light-years. The parallax of Alpha Centauri was larger, about 0.75 arcseconds, meaning it was closer, about 1.3 parsecs or 4.3 light-years. Vega's parallax was smaller still, putting it farther away. These measurements were revolutionary. For the first time, humans had a sense of the true scale of the stellar neighborhood. The nearest stars were not thousands of miles away, not millions, but trillions. The distances were staggering, and the method that revealed them, parallax, became the foundation of astronomical distance measurement. This is where the parsec enters the story. Astronomers needed a way to talk about these distances. They could have used any unit they wanted. They could have used miles or kilometers. They could have invented a new unit based on some convenient multiple of the Earth-Sun distance. They could have used light years from the start. But the natural unit for parallax work was the parsec. It emerged directly from the measurement technique. If you measured a star's parallax and got a certain number of arcseconds, You could immediately convert that to a distance in parsecs by taking the reciprocal. No multiplication by awkward conversion factors. No need to remember how many kilometers are in a light year. Just flip the number and you have your distance. This is not elegance in any deep sense, it is convenience. The parsec is not a fundamental unit of nature, it is a computational shortcut. It makes one particular calculation, the conversion from parallax angle to distance, as simple as possible. And that was enough. For 19th century astronomers, working without calculators or computers, simplifying calculations was not a trivial concern. Every saved step, every avoided multiplication, meant less chance of error and less tedious labour. The parsec saved time and reduced mistakes, so astronomers adopted it. Here is where things get interesting. The reasons for using the parsec have largely disappeared. Modern astronomers have computers that can handle any conversion instantly. The computational convenience that made the parsec attractive in 1838 is irrelevant in an age of digital calculation. And yet the parsec remains. This is not because astronomers are stubborn or ignorant. It is because the parsec has become embedded in the infrastructure of astronomy. Catalogues of stars list distances in parsecs. Scientific papers report distances in parsecs. Software assumes distances in parsecs. The Gaia spacecraft, which has measured the positions and distances of nearly 2 billion stars, reports its results in parsecs. Changing now would be enormously disruptive. Every old paper would need mental conversion. Every old catalogue would need translation. Every astronomer would need to retrain their intuition. The benefits of switching, whatever they might be, would not outweigh the costs. So the parsec persists, not because it is the best unit imaginable, but because it is good enough and it is already there. There is something almost comforting about this. Science is often portrayed as a realm of pure rationality, where the best ideas always win and inefficiencies are ruthlessly eliminated. But the persistence of the parsec suggests otherwise. Science is a human activity, and human activities accumulate history. They carry forward choices made long ago for reasons that may no longer apply, because changing would be more trouble than it is worth. This is not a failure. This is how complex systems work. They evolve incrementally, they build on what came before, they tolerate imperfection because perfection is expensive. But let us step back and consider what the parsec actually represents. A parsec is about 3.26 light years. A light year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. So a parsec is about 31 trillion kilometers. These numbers are already beyond ordinary human comprehension. We can write them down, we can compare them, but we cannot truly imagine them. The nearest star system to the Sun is Alpha Centauri, about 1.3 parsecs away. If you could somehow travel at the speed of a commercial airplane, about 900 kilometers per hour, it would take you about 4 million years to get there. At the speed of the fastest spacecraft humans have ever built, about 700,000 kilometers per hour, it would still take about 6,000 years. The Milky Way galaxy is about 30,000 parsecs across. The nearest large galaxy, Andromeda, is about 780,000 parsecs away. The observable universe extends to about 14 billion parsecs in every direction. These numbers are, in a very real sense, meaningless to the human mind. We do not have the intuitive machinery to grasp them. We can manipulate them mathematically, compare them, perform calculations with them, but we cannot picture them the way we picture the distance to the grocery store or the height of a mountain. This is one of the strange features of astronomy. The subject matter is so far removed from human experience that our normal intuitions are useless. The parsec is unintuitive, but so is every other unit of astronomical distance. A light year sounds more poetic, perhaps, because it involves light and time, two concepts we think we understand. But a light year is no more imaginable than a parsec. Both are simply labels for quantities that exceed our capacity for visualization. In a sense, the strangeness of the parsec is appropriate. It reminds us that we are dealing with a domain where strangeness is the norm. The universe does not care about human intuition. It operates on scales that our brains, evolved for navigating African savannas and tracking prey, were never designed to comprehend. Let us consider the light year for a moment. The light year seems more intuitive than the parsec. Light travels at a known speed, about 300,000 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers. This is the light year. It connects distance to time in a way that feels natural. But the light year was not the choice of working astronomers. It became popular in science communication, in textbooks, in popular writing about astronomy. Professional astronomers, doing actual research, preferred the parsec. This creates a curious split. When astronomers talk to the public, they often use light years because it is more familiar. When they talk to each other, they use parsecs because it is more practical. There are two parallel languages, one for insiders and one for outsiders. This is common in specialized fields. Doctors use medical terminology among themselves and simpler language with patients. Lawyers have their own vocabulary that differs from everyday English, but astronomy may be unusual in having two entirely different units of distance used in different contexts for what is fundamentally the same quantity. Why did the light year not replace the parsec, given its greater intuitive appeal? Part of the answer is timing. The parsec was established before the light year became popular. By the time light years gained currency in popular writing, parsecs were already entrenched in the professional literature. Part of the answer is practical. For parallax measurements, the parsec really is more convenient. The relationship between parallax and distance in parsecs is simple. The same relationship in light years involves a messier conversion factor. When you are doing the same calculation thousands of times, a simpler formula matters. And part of the answer is cultural. Astronomers learn the parsec in graduate school. They read papers in parsecs. They develop an intuition for parsecs. Switching to light years would mean relearning intuitions that took years to develop. This last point is worth dwelling on. We tend to think of scientific units as arbitrary labels, interchangeable as long as you do the conversions correctly. But in practice, scientists develop intuitions for the units they use. An astronomer who has worked with parsecs for decades knows without calculating that a few parsecs is the scale of the immediate stellar neighborhood, that a few thousand parsecs takes you across a significant chunk of the galaxy, that millions of parsecs puts you among the distant galaxies. These intuitions are valuable. They allow quick estimates, sanity checks, back-of-the-envelope calculations. Switching units would temporarily disable these intuitions, making work slower and more error-prone until new intuitions developed. So the parsec remains, not because it is objectively superior, but because it is subjectively familiar to those who use it. There is a broader lesson here about the relationship between tools and users. Tools shape the people who use them. A carpenter who works with hand tools develops different skills and different intuitions than one who works with power tools. A writer who composes on a typewriter develops a different process than one who writes on a computer. The tool influences the mind as much as the mind wields the tool. Astronomers have been shaped by the parsec. Their mental picture of the universe, their sense of scale and proportion, is calibrated in parsecs. This is not a deficiency, it is simply how expertise works. You internalize the tools of your trade and they become part of how you think. If astronomy had developed differently, if some alternative unit had become standard, astronomers would have different intuitions. They would picture the universe in different terms. The science itself would be the same, the stars and galaxies unchanged, but the mental apparatus for thinking about it would be different. This suggests that the choice of units is not entirely arbitrary. Different units encourage different ways of thinking. The parsec, tied to parallax and angular measurement, keeps astronomers connected to the observational roots of their science. The light year, tied to the speed of light and the passage of time, might encourage a more abstract theoretical perspective. Neither is better in any absolute sense. They are different tools, suited to different purposes. Let us now consider some other units in science that are similarly strange, similarly historical, similarly persistent. The astronomical unit, for instance. This is the average distance from the Earth to the Sun, about 150 million kilometers. It is used for distances within the solar system, where parsecs and light years would be awkwardly small. The astronomical unit is a bit arbitrary. It happens to be the size of Earth's orbit, which is not a fundamental constant of nature. If humans had evolved on Mars, our astronomical unit would be larger. If we had evolved on Venus, it would be smaller. The unit reflects our particular vantage point in the cosmos, not any inherent property of the universe. And yet, the astronomical unit persists. It is convenient for discussing planetary distances. It connects to human experience in the sense that it is the distance to our local star. It has been in use for centuries and is too entrenched to replace. Or consider the electron volt used in particle physics. An electron volt is the amount of energy gained by an electron when it moves through an electric potential of 1 volt. It is a tiny amount of energy, useful for discussing the energies of particles, photons, and atomic transitions. The electron volt is not a fundamental unit. It is defined in terms of human-created technology, the volt, which is itself defined in terms of other units. A purely rational system of units might use something different. But the electron volt is convenient, familiar, and embedded in decades of literature. It persists. Or consider the calorie used in nutrition. The calorie is technically a unit of energy, the amount needed to raise 1 gram of water by 1 degree Celsius. The nutritional calorie, confusingly, is actually a kilocalorie, 1,000 times larger. This is a mess. The unit is confusing, inconsistent with how energy is measured in physics, and tied to an outdated definition based on water. And yet it persists, because food labels use it, diet books use it, and replacing it would require retraining millions of people. Science is full of these relics, units that made sense in their original context, that became embedded in practice, and that now persist through inertia. The parsec is not unique. It is simply one example of a broader pattern. This pattern tells us something about how knowledge accumulates. We might imagine that science advances by constantly refining its tools, discarding the obsolete and adopting the optimal. But this is not quite right. Science advances by building on what came before. It inherits not just ideas, but also the apparatus for expressing those ideas. The vocabulary, the notation, the units of measurement. Changing these inherited tools is costly. It requires rewriting textbooks, retraining scientists, updating software, converting databases. These costs are real and substantial. They must be weighed against the benefits of the new tools. Often the benefits are not large enough. The old tools work. They may be inelegant, but elegance is a luxury. What matters is whether the tools allow work to proceed. If they do, they tend to persist. This is not irrationality, it is pragmatism. Science operates under constraints of time, money, and human attention. Optimizing everything is impossible. Instead, scientists optimize what matters most and tolerate imperfection elsewhere. The parsec is tolerable. It does not impede research. It does not introduce errors. It is simply a bit odd, a bit historical, a bit arbitrary. and so it remains. Let us return to the parallax measurement itself. For most of the history of parallax astronomy, measurements were made from the ground. Telescopes pointed at the sky, tracking stars over months and years, measuring their tiny shifts against the background. The precision was limited by the atmosphere, which blurs and distorts starlight, and by the stability of the instruments, which had to maintain their calibration over long periods. The parallaxes that could be measured were limited to the nearest stars. Beyond a few hundred parsecs, the shifts became too small to detect reliably. The vast majority of stars in the galaxy were beyond the reach of ground-based parallax measurements. This changed with the launch of the Hipparcos satellite in 1989. From space, above the atmosphere, Hipparcos could measure positions and parallaxes far more precisely than any ground-based telescope. Over its 4-year mission, it measured the parallaxes of about 120,000 stars, with accuracies of about 1 millisecond. 1 millisecond is a thousandth of an arcsecond. At that precision, you can measure distances out to about 1,000 parsecs. This was a dramatic expansion of the cosmic neighborhood accessible to parallax measurement. But the real revolution came with Gaia. The Gaia spacecraft, launched in 2013, has transformed parallax astronomy. Its precision is about 100 times better than Hipparcos for bright stars, and it has measured nearly 2 billion stars, compared to Hipparcos's 120,000. Gaia's parallaxes reach accuracies of tens of microarcseconds for the brightest stars. A microarcsecond is a millionth of an arcsecond. At that precision, you can measure distances of tens of thousands of parsecs, reaching across the galaxy and beyond. This is remarkable. A technique that was nearly impossible to achieve in 1838, that required the greatest astronomers of the age to measure a single star, can now be applied to billions of stars automatically by a spacecraft. The Parsec, born from the constraints of 19th century measurement, now labels distances determined by 21st century technology. The unit has not changed. The technique it serves has been transformed. There is something poetic in this continuity. The geometry is the same. The definition of the parsec is the same. But the scale of what can be measured has expanded by orders of magnitude. The same concept, applied with better tools, reveals a vastly larger universe. And the parsec, that historical relic, that computational convenience, remains the natural unit for expressing the results. Let us think about what Gaia's measurements actually mean. When Gaia measures a star's parallax, it is measuring the tiny apparent wobble in the star's position as Earth orbits the Sun. The wobble is caused by our changing perspective, just like the shift you see when you close one eye and then the other. For a star at 1 parsec, the wobble would be 1 arcsecond, but no star is that close to us except the Sun. The nearest star, Proxima Centauri, has a parallax of about 0.77 arcseconds, corresponding to a distance of about 1.3 parsecs. Most stars are much farther. A typical star in the Milky Way might be a few thousand parsecs away. Its parallax would be measured in milliarcseconds or microarcseconds. Detecting such tiny shifts requires extraordinary precision. Gaia achieves this precision by measuring each star's position hundreds of times over its mission. The spacecraft slowly rotates, sweeping its field of view across the sky. Each star is observed repeatedly at different times of year from different points in Earth's orbit. The accumulated data, analysed with sophisticated algorithms, yields parallaxes far more precise than any single measurement could achieve. The result is a 3-dimensional map of the Milky Way. For nearly 2 billion stars, we now know not just where they appear in the sky, but how far away they are. We can see the structure of our galaxy, the spiral arms, the central bulge, the streams of stars torn from ancient dwarf galaxies. All of this is expressed in parsecs, kiloparsecs for galactic structures, megaparsecs for distances to other galaxies. The unit scales up smoothly, carrying its historical origins into the realm of modern cosmology, but let us pause and consider what it means to measure a distance of, say, 10,000 parsecs. 10,000 parsecs is about 33,000 light-years. Light from a star at that distance left the star 33,000 years ago, when humans were still living in the Stone Age. The star we see is not the star as it is now, but as it was when our ancestors were painting on cave walls. For more distant objects, the time delay is even greater. The Andromeda Galaxy is about 780,000 parsecs away. The light we see from it left 2.5 million years ago, when early humans were just beginning to walk upright. Quasars, the luminous nuclei of distant galaxies, can be billions of parsecs away. Their light has been travelling for billions of years. We see them as they were when the universe was young. This is the strange reality of astronomical observation. We cannot see the universe as it is now. We can only see the universe as it was, at times determined by the distances to the objects we observe. The farther we look, the further back in time we see. The parsec, as a unit of distance, is also implicitly a unit of time delay. A parsec is about 3.26 years of light travel. 10 parsecs is about 33 years. 1,000 parsecs is about 3,260 years. The numbers encode not just spatial separation, but temporal separation. This is true of the light year as well, of course. But the parsec, with its origins in angular measurement, keeps the focus on the geometric relationship, on the apparent shift in position. The light year foregrounds the passage of time and the journey of light. Both are valid perspectives. They emphasize different aspects of the same underlying reality. Let us now think about why humans have so much trouble with large numbers. The human brain evolved to deal with quantities relevant to survival on the African savanna. We can intuitively grasp numbers up to a few dozen, maybe a few hundred. We can count the members of our tribe, the fruit on a tree, the days until the next full moon. But beyond a few thousand, our intuition fails. 1,000,000 is just a word. 1,000,000,000 is another word, slightly larger. We know intellectually that 1,000,000,000 is 1,000 times larger than 1,000,000, but we do not feel it. The numbers are too large to visualize. This creates problems for understanding the cosmos. The nearest star is about 40 trillion kilometers away. The Milky Way is about 100,000 light-years across. The observable universe is about 93 billion light-years in diameter. These numbers are not just large, they are incomprehensibly large. They exceed our capacity for intuition by so many orders of magnitude that they become meaningless abstractions. We can write them, calculate with them, compare them, but we cannot picture them. Astronomical units like the parsec do not solve this problem. A parsec is no more intuitive than 1,000,000,000,000 kilometers. But units do help in one way. They provide landmarks. If you work with parsecs regularly, you develop a sense of scale. You know that 1 parsec is nearby, the immediate stellar neighborhood. 10 parsecs is still close, within the solar vicinity. 1,000 parsecs takes you across a significant chunk of the galaxy. 1,000,000 parsecs puts you among the distant galaxies. These are not visual intuitions. You cannot picture 1,000 parsecs. But they are cognitive intuitions. You know where you are on the map, roughly speaking. You have reference points. This is how experts deal with large numbers in any field. Economists talk about billions and trillions of dollars. Biologists talk about billions of years of evolution. Particle physicists talk about energies measured in billions of electron volts. In each case, the numbers are beyond ordinary comprehension, but practitioners develop a working familiarity with them. The parsec is part of this working familiarity for astronomers. It is not intuitive in the sense of being visualizable, but it is intuitive in the sense of being familiar, of having associations and reference points, of fitting into a mental framework for thinking about cosmic distances. Let us consider the relationship between measurement and understanding. Measuring something does not mean you understand it. You can measure the distance to a star without understanding what a star is, how it shines, why it is where it is. Measurement provides data. Understanding requires interpretation, but measurement is often a precursor to understanding. Without knowing the distances to stars, we could not determine their true luminosities. Without knowing luminosities, we could not classify stars or understand their life cycles. Without understanding stellar life cycles, we could not know how elements are forged in stellar furnaces or how planets form from stellar debris. The parsec, as a unit of distance measurement, is at the foundation of this edifice of understanding. It is not glamorous. It does not directly reveal the nature of stars or the origin of the universe, but it provides one of the essential numbers, the distance, without which deeper understanding would be impossible. In this sense, the parsec is like a surveyor's unit. Surveyors measure land, dividing it into lots, establishing boundaries, determining elevations. The measurements themselves are mundane, but they enable everything that follows: construction, development, ownership, use. Astronomers are surveyors of the cosmos. They measure positions and distances, mapping the universe. The parsec is one of their tools. It enables the construction of knowledge about what the universe contains and how it is structured. Let us now think about the irony of the parsec's persistence. In 1838, when Bessel measured the parallax of 61 Cygni, he was working at the limit of what was possible. His instruments were the most advanced of their time, but they were still fundamentally simple: telescopes, micrometers, clocks. His calculations were done by hand, with pen and paper and perhaps a slide rule. The parsec made sense in that context. It simplified the crucial calculation. It fit the technology of the time. Today, astronomers have computers that can perform billions of calculations per second. They have spacecraft that measure positions to microarc-second precision. They have databases containing billions of stellar distances. The computational simplicity that motivated the parsec is irrelevant, and yet the parsec remains. There is something almost funny about this. We have advanced so far beyond the technological context in which the parsec was invented, yet we still use it. We fly robots to Mars, but we measure stars with a unit designed for pencil and paper calculation. But this irony is not a critique. It is an observation about how systems evolve. The parsec has survived not because it is optimal, but because it is adequate. It does the job. It causes no problems, and the cost of replacing it would exceed any benefit. This is how many things persist in human systems. Institutions, practices, conventions, they continue because they work well enough, and changing them would be too disruptive. The parsec is no different from the QWERTY keyboard, or the standard railroad gauge, or the division of the hour into 60 minutes. All are historical artifacts, optimized for conditions that no longer exist, yet still in use because the cost of change exceeds the cost of continuation. There is wisdom in this, even if it looks like inertia. Change for its own sake is not a virtue. Consistency has value. Familiarity has value. The parsec, by remaining constant while everything around it has changed, provides continuity. Astronomers in 1838 and astronomers in 2024 speak the same language of distance. They can read each other's work. They share a framework. This continuity is not nothing. It is part of what makes science cumulative. Each generation builds on the work of previous generations. That building requires a common foundation, a shared vocabulary, a consistent set of concepts. The parsec is part of that foundation. Let us now take a long view. The parsec was invented in the 19th century. It has now been in use for nearly 200 years. How much longer will it last? Predicting the future is always uncertain, but some trends are visible. Space-based parallax measurements, like those from Gaia, have revolutionized the field. Future missions will extend the reach and precision of parallax even further. As long as parallax remains a primary method for measuring distances, the parsec will remain relevant. Its computational convenience may be obsolete, but its conceptual connection to the measurement technique is not. If some new method of distance measurement becomes dominant, one that does not rely on parallax, the parsec might gradually fade. But such a method would need to be applicable to a wide range of objects and distances, better than parallax in some significant way. No such method is currently on the horizon. More likely, the parsec will continue for the foreseeable future. It may eventually become an archaism, like the chain or the furlong, units that persist in specialized contexts but are not widely known. But even then, it will be part of the historical record. Astronomers in 1,000 years, if they still exist, may still read papers in parsecs. This long persistence is not unique to the parsec. Many units have survived for centuries. The mile, the pound, the gallon, these are old units that continue in use despite the availability of metric alternatives. Cultural inertia is powerful. Once a unit is established, it tends to persist. The parsec will likely follow this pattern. It will be with us for a long time, a reminder of 19th century astronomy embedded in 21st century science. Let us reflect on what all of this tells us about science. Science is often portrayed as a revolutionary activity, overturning old ideas, replacing the obsolete with the new. And sometimes it is. The history of science includes genuine revolutions, moments when old frameworks were swept away and new ones took their place. But most of the time, science is conservative. It preserves what works. It changes slowly, incrementally, building on what came before. The revolutionary moments are rare, the conservative work is constant. The parsec exemplifies this conservative side of science. It is not revolutionary, it is traditional. It connects modern astronomy to its 19th century roots. It embodies continuity rather than rupture. Both aspects of science are necessary. Revolution without conservation would be chaos, a constant reinvention of the wheel. Conservation without revolution would be stagnation, a refusal to improve. The balance between them is what allows science to progress while maintaining coherence. The parsec sits firmly on the conservative side. It is part of what is preserved, part of the continuity that makes cumulative progress possible. It is not glamorous, but it is valuable. Let us now think about the experience of learning astronomy. When a student first encounters the parsec, it is often confusing. Why this strange unit? Why not just use light years, which seem more intuitive? Why do astronomers make things complicated? These are reasonable questions. The answers, as we have seen, involve history, convenience, and the accumulated weight of tradition. But for a student just beginning, these answers may not be satisfying. The parsec seems like an arbitrary obstacle, something to memorize rather than understand. Over time, with practice, the confusion fades. The student becomes comfortable with parsecs. They develop a sense of scale, an intuition for what different numbers mean. The parsec becomes part of their mental toolkit, no longer strange but familiar. This is how all expertise develops. What seems arbitrary and confusing to the beginner becomes natural and obvious to the expert. The tools of a trade are internalized, becoming second nature. The parsec is one of these tools for astronomers. It is strange at first, then familiar, then invisible. The student who once struggled with it eventually uses it without thinking, just as the carpenter uses the hammer without reflecting on its history. This process of internalization is part of what makes expertise possible. We cannot constantly reflect on our tools. We must use them automatically, freeing our attention for higher-level tasks. The Parsec, once internalized, frees astronomers to focus on the science rather than the units. Let us consider the relationship between the Parsec and other distance indicators. Parallax is the gold standard for distance measurement in astronomy, but it only works for relatively nearby objects. Beyond a few thousand parsecs, the parallax shifts become too small to measure reliably, even with the best instruments. For more distant objects, astronomers use other techniques. Standard candles are objects of known intrinsic brightness. By comparing their apparent brightness to their known luminosity, you can calculate their distance. Cepheid variable stars, with their predictable pulsation periods, are one type of standard candle. Type Ia supernovae, with their consistent peak luminosities, are another. These techniques extend the distance ladder far beyond what parallax can reach. Cepheids can be seen in nearby galaxies, millions of parsecs away. Supernovae can be seen across the observable universe, billions of parsecs away. But here is the connection. The calibration of these techniques depends on parallax. To know the intrinsic brightness of a cepheid, you need to measure the distances to nearby cepheids directly using parallax. Those parallax distances are the foundation on which the entire distance ladder rests. And those parallax distances are measured in parsecs. The calibration that enables us to measure the most distant objects in the universe is grounded in the same unit that was invented for local stellar measurements in 1838. This is another reason the parsec persists. It is not just used for parallax measurements themselves. It is embedded in the calibration of other techniques. The entire system of cosmic distance measurement is built on a foundation expressed in parsecs. Changing the unit would mean recalibrating everything. Every standard candle relationship, every distance ladder rung would need to be re-expressed in new terms. The disruption would propagate throughout the field. And for what benefit? The distances themselves would not change. The universe would be the same size. Only the labels would differ. The cost of change would be real. The benefit would be purely cosmetic. So the parsec remains, anchoring the distance ladder, connecting local measurements to cosmic scales. Let us think about the philosophy of scientific units more broadly. Units are a form of language. They are conventions that allow us to communicate quantitative information. Like words, they are arbitrary in their origins, but powerful in their effects. The word tree does not resemble a tree. It is just a sound, a sequence of letters that English speakers have agreed to associate with a certain kind of plant. Similarly, the parsec does not resemble a distance. It is just a unit, a convention that astronomers have agreed to use. But once established, these conventions shape thought. The words we use influence how we think about the world. The units we use influence how we think about quantities. Astronomers who think in parsecs have a particular mental geography of the cosmos. They know that 1 parsec is close, 1,000 parsecs is far within the galaxy, 1,000,000 parsecs takes you to other galaxies. This mental map is calibrated in parsecs. If they thought in light years, the numbers would be different, but the mental map would have the same structure. The nearby would still be nearby, the distant still distant. The map would be translated, not transformed. But translation is not nothing. Different units emphasize different aspects of reality. The light year emphasizes time and the finite speed of light. The parsec emphasizes geometry and angular measurement. These different emphases might lead to subtly different ways of thinking about cosmic distances. This is speculative, of course. We cannot easily compare the thinking of astronomers who use different units because almost all astronomers use the same units. But the possibility is intriguing. Units might be more than mere labels. They might be cognitive tools that shape understanding in subtle ways. Let us consider the parsec in the context of the metric system. The metric system was designed to be rational, coherent, and universal. It is based on powers of 10. It uses a consistent set of prefixes. It is meant to replace the hodgepodge of traditional units that varied from country to country and trade to trade. The parsec does not fit neatly into the metric system. It is not a power of 10 times anything. It is not derived from the fundamental metric units of length. It is an astronomical peculiarity existing outside the tidy structure of meters and kilometers. In principle, astronomers could express distances in meters. A parsec is about 3.09 times 10 to the 16th meters. This is a perfectly valid way to express the distance, but it is cumbersome. The numbers are unwieldy. The metric system, designed for human-scale quantities, becomes awkward at cosmic scales. This is why astronomers use specialized units. The metric system is not well suited to the domain. Its strengths, coherence, and universality become weaknesses when the quantities involved are trillions of times larger than everyday experience. The parsec, the light year, the astronomical unit, these are adaptations to the peculiar demands of astronomy. They sacrifice the universality of the metric system for the convenience of the domain. This trade-off is reasonable, even necessary, given the scales involved. So the parsec coexists with the metric system, used alongside it rather than integrated into it. Astronomers are fluent in both languages, switching as needed between the metric units of laboratory physics and the specialized units of their own field. Let us now consider the human side of science once more. Science is often presented as impersonal, as a machine that produces knowledge independently of the humans who practice it. But this is a distortion. Science is deeply human. It is done by humans, for humans, using human tools and concepts. The parsec is a reminder of this humanity. It is not a discovery about the universe. It is an invention, a human creation, designed to meet human needs. It bears the marks of its origins, the fingerprints of 19th century astronomers who needed a convenient way to express distances. These fingerprints do not diminish the science. They contextualize it. They remind us that knowledge is always produced in a context, shaped by the circumstances of its production. Future generations might look back at our science and see similar fingerprints. They might wonder why we measured things the way we did, why we used the concepts we used, why we organized knowledge as we did. Our choices, which seem natural to us, might seem arbitrary to them. This is not relativism. The facts of science are not arbitrary. The universe is what it is, regardless of how we describe it. But the descriptions, the frameworks, the units, these are human choices. They could have been otherwise. They are contingent rather than necessary. The parsec embodies this contingency. It is one choice among many possible choices. It has persisted not because it was inevitable, but because it was made and then maintained. It is a monument to the path not taken, a reminder of what might have been different. Let us think about the experience of using a unit over a long period. An astronomer who has worked for decades has used the parsec thousands of times. They have read papers in parsecs, written papers in parsecs, discussed distances in parsecs. The unit has become part of their intellectual identity. Such an astronomer does not experience the parsec as strange. They experience it as natural, as the obvious way to express distance. The strangeness that a beginner feels has long since evaporated. This is the power of habituation. With enough exposure, anything can become normal. The parsec, which seems so odd to the uninitiated, becomes mundane to the practiced. But habituation is not understanding. The astronomer who uses parsecs fluently might not be able to explain their history or justify their persistence. They simply use them as they use language without constant reflection on origins and alternatives. This is fine. Constant reflection would be paralyzing. We cannot justify every choice, examine every assumption, question every tool. We must accept much on trust and get on with the work. The Parsec is accepted on trust by most astronomers. They learned it as students, use it as professionals, and will pass it on to the next generation. The cycle continues, the unit persisting through transmission rather than reinvention. Let us consider the alternative units that exist but are rarely used. In addition to parsecs and light years, there are other units of cosmic distance. The Siriometer, for instance, was proposed as the distance to Sirius, about 2.6 parsecs. It never caught on. The light second, light minute, and light hour are occasionally used for distances within the solar system, but they are not standard. The astronomical unit dominates that domain. For very large distances, megaparsecs and gigaparsecs are used. A megaparsec is 1,000,000 parsecs, about 3.26 million light-years. A gigaparsec is 1,000,000,000 parsecs. These are convenient for discussing the scale of the universe, where individual parsecs would be lost in the noise of large numbers. The prefixes mega and giga integrate the parsec into a quasi-metric structure. Astronomers can scale up smoothly from parsecs to kiloparsecs to megaparsecs to gigaparsecs, covering the entire range of cosmic distances. This scalability is one of the parsec's advantages. It works at all scales, from the nearest stars to the edge of the observable universe. Different prefixes adapt it to different contexts, but the base unit remains the same. The light year has similar scalability. You can speak of kilo light years or mega light years, though these terms are less common in professional use. The parsec's dominance in professional astronomy means that its prefixed forms are more widely used. Let us now think about the role of tradition in science. Tradition is sometimes seen as the enemy of progress. The old ways are obstacles to be overcome, shackles to be broken. Innovation requires discarding the past, but tradition also has value. It preserves what has been learned. It provides continuity. It saves each generation from having to reinvent everything from scratch. The Parsec is part of astronomical tradition. It connects current astronomers to their predecessors. It is a link in a chain that extends back nearly 2 centuries. This tradition is not static. Astronomy has changed enormously since 1838. The techniques, the technologies, the theories, all have been transformed. But the Parsec remains, a thread of continuity through all the change. Traditions can be good or bad, helpful or harmful. They must be evaluated, not blindly followed. But the Parsec, evaluated on its merits, is a good tradition. It works. It serves its purpose. It does not impede progress. Not all traditions are like this. Some are genuinely harmful and should be discarded. But the Parsec is benign. It is a tradition worth keeping, not because it is traditional, but because it is effective. Let us consider what astronomy might look like to an outside observer. Imagine an intelligent being from another world examining human astronomy. They would see a sophisticated science capable of measuring distances to stars and galaxies, of detecting gravitational waves, of mapping the cosmic microwave background. But they might also notice something odd. These advanced scientists measure distances using a unit based on the geometry of their planet's orbit. They have units named after phenomena, like the year, that are specific to their particular world. Their science is parochial in its language, even as it is universal in its reach. This is an interesting juxtaposition. The content of astronomy is universal. The laws of physics are the same everywhere. The stars and galaxies are the same whether observed from Earth or from some other vantage point. But the language of astronomy, the units and conventions, is particular to Earth. An alien astronomer would use different units. Their version of the parsec, if they had one, would be based on their planet's orbit, not ours. Their light year would be based on their year, not ours. The numbers would all be different, but the science would be the same. The distances to stars, translated into whatever units the aliens used, would correspond to the same physical separations. The universe does not care what units we use to describe it. This thought experiment highlights the arbitrariness of units. They are human conventions, useful for communication, but not fundamental to the reality they describe. The parsec is our convention. It could have been otherwise. Let us return to Earth and consider the present moment. Right now, somewhere in the world, an astronomer is using the parsec. They are analyzing data, writing a paper, giving a talk, teaching a class. The parsec is part of their work, as natural to them as any other tool. They might not think about the parsec's history. They might not reflect on its persistence. They simply use it as they use language, as they use mathematics, as they use all the inherited tools of their trade. This everyday use is the ultimate justification for the parsec. It is used because it is useful. It persists because it works. The abstract questions about history and philosophy fade into the background when there is work to be done. And there is always work to be done. The universe is vast and mostly unexplored. Every measurement, every observation, every analysis brings us a little closer to understanding. The parsec is part of this ongoing project, a small but necessary component of the scientific enterprise. Let us consider the poetry of measurement. Measurement might seem prosaic, the opposite of poetry. Numbers and units, precision and calibration, these are not the stuff of lyric verse. But there is a kind of poetry in measurement nonetheless. The act of reaching out to the stars, of quantifying the unimaginable, of pinning down the ineffable with numbers, this has a grandeur of its own. The parsec, strange as it is, participates in this grandeur. It is a human attempt to grasp the cosmos, to bring the vast and distant within the reach of understanding. It may be imperfect, but it is an attempt. It is better than silence, better than resignation, better than admitting defeat before the immensity of space. When an astronomer reports that a star is 10 parsecs away, they are doing something remarkable. They are connecting a point of light in the night sky to a specific location in three-dimensional space. They are placing that star on a map, giving it a position, integrating it into our knowledge of the cosmos. This is not nothing. This is the slow, patient work of understanding. Each measurement adds a bit more to the picture. Each parsec of distance, determined and recorded, fills in a bit more of the map. The parsec is a humble unit. It does not call attention to itself. It is just a label, a convention, a tool. But it participates in something larger, in the human project of understanding the universe. Let us now bring things toward a close. We have ranged widely, from the geometry of parallax to the philosophy of scientific units, from the history of 19th century astronomy to the mission of the Gaia spacecraft. Through it all, the parsec has been our thread, our guide, our object of contemplation. What have we learned? We have learned that the parsec exists for historical reasons, born from the needs of astronomers measuring parallax with pencil and paper. We have learned that it persists for practical reasons, embedded in the literature and infrastructure of astronomy. We have learned that it is strange, but not uniquely strange, one of many scientific conventions that carry the marks of their origins. We have learned that science is a human activity, shaped by history, constrained by practicality, tolerant of imperfection. The parsec is a reminder of this humanity, a fingerprint of 19th century astronomers on 21st century science. We have learned that units are not just labels, but cognitive tools, shaping how we think about the quantities they measure. The parsec, tied to parallax and angular measurement, keeps astronomers connected to the observational roots of their science. And we have learned that the persistence of the parsec is not a failure, but a feature. It represents continuity, stability, the preservation of what works. It is part of the foundation on which cumulative progress is built. The parsec is not elegant. It is not intuitive. It is not what we would design if we were starting from scratch. But we are not starting from scratch. We are inheriting a tradition, building on what came before, making do with imperfect tools. And the tools work. The parsec works. It has worked for nearly 2 centuries and will likely work for centuries more. It is adequate to its purpose, embedded in its context, familiar to its users. This is enough. There is a kind of wisdom in accepting imperfect tools. The pursuit of perfection can be paralyzing. The ideal can be the enemy of the good. Sometimes the best choice is to use what is available and get on with the work. The parsec embodies this wisdom. It is not perfect, but it is available. It is not ideal, but it is good enough. And so it is used day after day, year after year, generation after generation. Let us end with a simple thought. The universe is vast. We are small. Our tools are imperfect, our understanding incomplete, our reach limited. And yet we reach, we measure, we quantify, we build slowly a picture of the cosmos. The parsec is part of this reaching. It is a way of talking about distances that exceed our imagination, a way of bringing the unreachable within the scope of thought. It is a strange unit, but strangeness is not a flaw. It is a reflection of the strangeness of the enterprise, of trying to measure a universe that dwarfs us in every dimension. We do what we can with what we have. The parsec is what we have, and with it, with this strange, historical, imperfect unit, we have mapped the positions of nearly 2 billion stars, measured the scale of galaxies, traced the structure of the cosmos. Not bad for a unit invented to simplify pencil and paper calculations. The universe does not care what units we use. It is what it is, regardless of our conventions. But we care. We are the ones who need to communicate, to collaborate, to build on each other's work. We are the ones who need units. The parsec serves us. It has served us for a long time. It will continue to serve as long as we need it, as long as we find it useful. And when we no longer need it, if that day ever comes, it will fade gently into history. A footnote, a curiosity, a reminder of how things once were done. But that day is not today. Today, the parsec is alive. It is used. It is part of the ongoing work of understanding the cosmos. And that is enough. The next time you look up at the night sky, consider this. Every star you see has a distance. That distance can be measured, has been measured for many stars, and is expressed in parsecs. The light that reaches your eyes left those stars years or decades or centuries ago, and the distances it has travelled are encoded in the tiny shifts of parallax, the wobbles that reveal how far away they are. The parsec is the unit of those distances. It is our way of talking about them, of thinking about them, of placing the stars on the map. It is a strange unit, but the universe is strange. Perhaps they deserve each other. The stars shine on, indifferent to our measurements, but we measure anyway. We reach out with our instruments and our calculations, trying to grasp what cannot be touched. The parsec is part of that reaching. It is part of how we make sense of the vastness. It is part of being human in a cosmos that did not ask for us but got us anyway. And so we measure. In parsecs, because that is how it is done, because that is the tradition we inherited, because it works. Strange, imperfect, human, effective, the parsec, still here after nearly 200 years, still doing its job, still part of how we understand the universe. That is something worth noticing, even if it does not quite merit celebration. It is a quiet persistence, a gentle endurance, a modest but real contribution to human knowledge. The Parsec asks nothing of us. It simply exists, ready to be used when needed, waiting patiently in the toolbox of astronomy. And when we reach for it, it is there. As it has always been, as it likely always will be, for as long as we remain curious about the stars. This is the story of the Parsec, not a grand narrative of discovery and triumph, but a small story of convention and persistence. A story about how science actually works, in the details, in the compromises, in the choices that seem arbitrary but turn out to matter. The Parsec is not important in itself, no unit is, but it is part of something important, part of the apparatus of understanding, part of the human project of making sense of the cosmos. And that, in the end, is enough to make it worth knowing about, worth thinking about, worth perhaps a moment of quiet appreciation. The Parsec, a strange unit for a strange universe, ours to use, ours to inherit, ours to pass on. The chain continues, the tradition persists, the work goes on, and somewhere right now, an astronomer is typing a distance in parsecs, adding one more measurement to the vast catalogue of human knowledge about the stars. They probably do not think about any of this. They probably just type the number and move on. And that is fine. That is how it should be. The best tools are invisible, taken for granted, simply used. The Parsec is one of those tools, invisible to its users, essential to their work, a strange, humble, effective, persistent unit. The Parsec, still here, still working, still part of how we measure the universe, and that is a good place to end, not with a grand conclusion, but with a simple observation. The Parsec exists. It is used. It works. Sometimes that is all a unit needs to be. DB chaos, a constant reinvention of the wheel. Conservation without revolution would be stagnation, clinging to ideas that no longer work. The Parsec sits comfortably on the conservative side. It is not broken. It does not need fixing. It just quietly does its job, year after year, paper after paper, while the flashier parts of astronomy grab the headlines. There is something almost reassuring about this. Amid all the discoveries, all the new phenomena, all the revisions to our understanding of the cosmos, the Parsec remains. It is a fixed point, a familiar landmark, a reminder that not everything changes all the time, and perhaps that is part of its value. In a field where new results constantly challenge old assumptions, where today's breakthrough might be tomorrow's correction, the Parsec offers stability. It is the same unit it was in 1838. It will be the same unit in 2138. That constancy, boring as it might seem, is actually rather comforting. Let us think for a moment about how the Parsec scales. A single parsec is already a vast distance. But astronomers routinely deal with distances far larger. They need ways to talk about the scale of galaxies, of galaxy clusters, of the observable universe itself. For this, they use prefixes. A kiloparsec is 1,000 parsecs. A megaparsec is 1,000,000 parsecs. A gigaparsec is 1,000,000,000 parsecs. These are the units of cosmology. The Milky Way is about 30 kiloparsecs across. The distance to the Andromeda Galaxy is about 780 kiloparsecs, or 0.78 megaparsecs. The Virgo cluster, the nearest large cluster of galaxies, is about 16 megaparsecs away. The observable universe extends to about 14 gigaparsecs in every direction. Notice something odd here. We started with a unit designed for measuring distances to nearby stars, distances of a few parsecs, and now we are using the same unit, scaled up by factors of millions or billions, to measure the entire observable universe. This is a bit like using inches to measure the distance to the moon. You could do it, The moon is about 15 billion inches away, but it feels strange, stretching a small unit far beyond its original purpose. And yet astronomers do exactly this with the Parsec. They measure galaxies in kiloparsecs, intergalactic distances in megaparsecs, cosmic scales in gigaparsecs. The unit scales up smoothly, mathematically, but conceptually there is something almost absurd about it. A megaparsec is about 3.26 million light-years. A gigaparsec is about 3.26 billion light-years. These are not numbers that connect to any human experience. They are pure abstraction, labels for quantities that exceed imagination. But here is the thing. Any unit would be pure abstraction at these scales. A million light-years is no more imaginable than a megaparsec. A billion kilometers is no more graspable than a trillion. Once you get beyond a certain point, the numbers are just numbers. The unit does not matter because the quantity is incomprehensible either way. So astronomers use what they have. They use parsecs, kiloparsecs, megaparsecs, gigaparsecs. The unit is arbitrary, but so would be any alternative. And at least the parsec connects to the historical tradition of parallax measurement, even if parallax is no longer relevant at cosmological scales. This is another example of a tool outliving its original purpose. The parsec was invented for measuring distances to nearby stars. Now it measures distances to the edge of the observable universe. The purpose has changed, but the tool remains. There is something almost poetic about this. A unit born from the geometry of Earth's orbit, from the patient work of 19th century astronomers measuring tiny angular shifts, now labels the largest distances humans have ever contemplated. The parsec has travelled far from home. Let us consider how astronomers actually experience these units. When you work in a field long enough, its units become second nature. A chef knows intuitively what a tablespoon looks like. A carpenter knows what an inch feels like. The units are not abstract numbers. They are felt quantities connected to experience and practice. Astronomers develop a similar intuition for parsecs. Not a visual intuition, of course. No one can picture a parsec, but a cognitive intuition, a sense of where different numbers fit in the scheme of things. A few parsecs is the immediate neighbourhood, the nearest stars. This is the scale of parallax measurements, of stellar companions, of the sun's local environment. An astronomer hears a few parsecs and thinks, close by, practically next door. A few hundred parsecs is still local, but getting further out. This is the scale of star clusters, of stellar associations, of the nearby spiral arm. An astronomer hears a few hundred parsecs and thinks, our part of the galaxy, but not our backyard. A few thousand parsecs is galactic scale. This is where you start to see the structure of the Milky Way, the spiral arms, the bulge, the halo. An astronomer hears a few thousand parsecs and thinks, galaxy-wide, serious distance. Beyond 10,000 parsecs, you are getting to the far side of the galaxy, or beyond it entirely. This is where extragalactic astronomy begins, the realm of other galaxies, of cosmic structure. This intuitive scale is what astronomers would lose if they switched units. It is not just a matter of recalculating numbers. It is a matter of relearning where everything fits, rebuilding the mental map that years of experience have created. Imagine asking a chef to think in milliliters instead of tablespoons. The conversion is straightforward. A tablespoon is about 15 milliliters, but the intuition is lost. The chef no longer knows at a glance how much is enough. They have to think, to calculate, to rebuild their sense of proportion. Astronomers face the same problem, but worse. Their distances span a range of 12 orders of magnitude or more. Their intuitions are hard-won, developed over years of reading papers, analysing data, thinking about the cosmos. Switching units would scramble all of this. So they do not switch. They keep the parsec, with all its historical baggage, because the cost of switching is too high. The parsec is not just a unit, it is a framework for thinking, and frameworks are not easily replaced. Here is something gently amusing to consider. The parsec is defined in terms of the arcsecond, which is defined in terms of the degree, which is defined in terms of the full circle. A full circle has 360 degrees. This is not a natural number. It is a historical artifact inherited from the Babylonians, who used a base 16 number system. So the parsec, this unit of cosmic distance, ultimately traces back to the mathematical preferences of ancient Mesopotamia. The Babylonians, who lived thousands of years ago and knew nothing of stars beyond the naked eye, inadvertently shaped how we measure the universe today. This is the kind of historical entanglement that pervades all of science. No unit, no concept, no technique exists in isolation. Everything is connected to everything else, often in unexpected ways. The parsec carries within it the ghost of Babylonian mathematics. It is a strange thought, but not an unpleasant one. It reminds us that science is a cumulative enterprise built on the work of countless generations, each contributing something that the next generation inherits and builds upon. We are all, in a sense, working with Babylonian tools, even when we measure the farthest reaches of the cosmos. Let us think about what it would actually take to replace the parsec. First, you would need agreement. The astronomical community would have to decide collectively to adopt a new unit. This would require discussions, debates, votes, consensus. Scientists are not known for quick agreement on anything. The process could take years. Second, you would need a transition period. Old papers would still be in parsecs. New papers would be in the new unit. For a generation or more, astronomers would need to be bilingual, fluent in both systems. This is manageable but annoying. Third, you would need to update software. Astronomical databases, analysis tools, simulation codes, all of them assume parsecs. Rewriting this software would be a massive undertaking, consuming time and resources that could be spent on actual science. Fourth, you would need to retrain intuition. As we discussed, astronomers think in parsecs. Retraining this intuition would take years for each individual and a generation for the community as a whole. All of this for what benefit? The new unit would not enable any new science. It would not reveal any new phenomena. It would just be a different label for the same quantity. The cost-benefit analysis is clear. The costs are high and real. The benefits are low and mostly aesthetic. No rational community would make this trade. And so the parsec remains, not because anyone actively defends it, not because it has passionate advocates, simply because the alternative is worse. This is how many things persist in human systems, not through active support, but through the absence of a compelling reason to change. The parsec is the default, and defaults are powerful. Let us consider another angle. The parsec is sometimes criticized for being unintuitive, and it is. A light year, by contrast, seems more intuitive. Light travels at a known speed. A light year is the distance light covers in 1 year. This feels more grounded, more connected to physics. But is the light year really more intuitive? Consider what it actually means. Light travels at about 300,000 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers. This is the light year. Can you picture 9.46 trillion kilometers? Can you imagine light traveling for a year? The speed of light is so far beyond human experience that it is no more intuitive than the parsec. We cannot perceive it, cannot feel it, cannot relate it to anything in our everyday lives. The light year feels more intuitive because it involves familiar concepts: light, years, distance, time. We know what light is. We know what a year is. So the definition feels accessible, even if the quantity it defines is not. But this is a kind of illusion. The familiarity of the components does not make the whole any more comprehensible. A light year is just as unimaginable as a parsec. We just think we understand it better because the words are friendlier. This is worth noticing. Our sense of what is intuitive or natural is often superficial. We respond to surface features, to familiar words and concepts, rather than to the underlying quantities. The light year sounds more human-scaled because it mentions light and years, but it is no more human-scaled in reality. The parsec, with its awkward definition involving arcseconds and parallax, at least does not pretend to be intuitive. It wears its technicality openly. In a way, this is more honest. Let us think about how different units shape thinking. We mentioned earlier that different units encourage different ways of thinking. The parsec, tied to parallax and angular measurement, keeps astronomers connected to the observational roots of their science. The light year, tied to the speed of light and the passage of time, emphasizes the cosmic speed limit and the time delay inherent in observation. Neither perspective is wrong. Both capture something true about astronomical distance, but they emphasize different aspects. An astronomer thinking in parsecs is implicitly thinking about how distances are measured. The unit reminds them that distance, in astronomy, is derived from observation, from the careful measurement of positions and angles. This is a grounded perspective, rooted in empirical practice. An astronomer thinking in light years is implicitly thinking about light travel time. The unit reminds them that seeing a distant object means seeing into the past, that the universe we observe is not the universe as it is now. This is a more theoretical perspective, emphasizing the physics of light and time. Both perspectives are valuable. Both are true. The choice of unit subtly influences which perspective is foregrounded. Most astronomers are fluent in both. They can switch between parsecs and light years as needed, depending on context and audience. The two units coexist, each suited to different purposes. But in professional work, parsecs predominate. The reasons are practical: computational convenience in the past, continuity with the literature, established intuition. But there may also be a cultural preference for the observational perspective, for staying close to the data, for remembering that all our knowledge of distant objects comes ultimately from the faint light they send our way. Let us take a moment to appreciate something. We have been talking about the parsec as if it were a problem to be solved, an awkwardness to be explained. But perhaps we should step back and appreciate what it represents. The parsec exists because humans figured out how to measure the distances to stars. This is remarkable. For most of history, the stars were simply points of light in the sky. Their distances were unknown, unknowable. Philosophers debated whether they were pinholes in a celestial sphere or distant suns like our own. No one could settle the question. Then, in the 19th century, astronomers developed instruments precise enough to detect the tiny wobble of stellar parallax. They measured for the first time the actual distances to other stars. They discovered that the stars are suns, scattered across a vast three-dimensional space. The parsec is a product of this achievement. It is the unit that emerged from the measurement technique that finally answered an ancient question. Its awkwardness is the awkwardness of reality, the geometry of Earth's orbit reflected in a unit of distance. We could wish for a more elegant unit, but elegance was not the point. The point was to measure something that had never been measured before. The parsec was what emerged from that effort. There is something admirable in this. Science is not always elegant. It is often messy, contingent, shaped by circumstances. The parsec is a product of that messiness. It works because it emerged from the work itself, from the practical needs of astronomers doing a difficult job. Let us consider the specific case of the Gaia mission. Gaia is a European Space Agency spacecraft that has transformed our knowledge of the Milky Way. It has measured the positions, distances, and motions of nearly 2 billion stars, creating a three-dimensional map of unprecedented detail. Gaia's data are reported in parsecs, more precisely, in units derived from parsecs. Parallaxes are given in milliarc seconds, which convert directly to distances in kiloparsecs. Proper motions, the apparent movements of stars across the sky, are given in milliarc seconds per year. This is the natural language of the mission. Gaia measures angles. Angles convert to parsecs. The entire data pipeline, from raw observations to final catalogue, is structured around this system. If astronomers wanted to switch to light years, they would have to add a conversion step to every Gaia analysis. Not impossible, but unnecessary. The parsec system works smoothly with the data as it comes. This is the practical reality of modern astronomy. The parsec is not just a historical artifact. It is built into the infrastructure, the software, the workflows. It is the native language of the most important stellar survey ever conducted. And so the parsec will remain relevant for as long as Gaia data are analysed, which will be decades at least. The mission has guaranteed the parsec's future, not through any deliberate choice, but simply by using it. Let us think about the relationship between precision and units. Gaia measures parallaxes to precisions of tens of microarc seconds for bright stars. This is extraordinary. A microarc second is a millionth of an arc second. It is the angle subtended by a human hair at a distance of 1,000 kilometers. At this precision, systematic errors become important. Tiny imperfections in the spacecraft, subtle biases in the data processing can affect the results. Astronomers have spent years understanding and correcting these effects. The unit of measurement, the parsec, plays a role in this. Because distances are derived directly from parallaxes, any error in the parallax propagates to the distance. A parallax that is too small by 1% gives a distance that is too large by about 1%. The relationship is direct and transparent. This transparency is valuable. It allows astronomers to understand exactly how errors propagate, to trace problems back to their sources, to assess the reliability of their results. The parsec, by keeping the connection to parallax explicit, facilitates this kind of error analysis. A different unit, derived from parallax by a more complex conversion, would obscure this connection. The error propagation would be less obvious. Mistakes would be harder to catch. This is another reason the parsec persists. It is not just convenient, it is epistemically clean. It keeps the relationship between observation and inference visible and tractable. Let us now consider a different kind of distance measurement. Parallax works for nearby stars, out to a few kiloparsecs with current technology. But the universe is much larger than this. How do we measure distances to objects beyond the reach of parallax? The answer is a series of techniques, each building on the last, forming what astronomers call the cosmic distance ladder. The first rung is parallax. This gives direct distances to nearby stars. From these, we can calibrate other methods. The second rung uses standard candles. These are objects of known intrinsic brightness. By comparing how bright they appear to how bright they actually are, we can calculate their distances. Cepheid variables, a type of pulsating star, are one important standard candle. Their pulsation period correlates with their luminosity, allowing their true brightness to be determined from observation. The third rung uses type Ia supernovae. These are stellar explosions of remarkably consistent brightness. They can be seen across vast distances, extending the distance ladder to billions of parsecs. Each rung depends on the previous one. Parallax calibrates the cepheids. Cepheids calibrate the supernovae. Errors at any stage propagate upward, affecting all subsequent measurements. Notice that the parsec appears throughout. Parallax distances are in parsecs. Cepheid distances are in parsecs. Supernova distances are in megaparsecs or gigaparsecs. The unit is the common language of the entire ladder. If astronomers switched units partway up the ladder, they would create unnecessary confusion. The calibrations would need conversion. The error analysis would become more complex. The parsec, by staying constant throughout, provides continuity. This is another reason for its persistence. The cosmic distance ladder is the foundation of extragalactic astronomy. Changing its units would require rebuilding that foundation piece by piece. No one wants to do this. Let us think about what happens at the very largest scales. Beyond a few hundred megaparsecs, distances become entangled with cosmology. The universe is expanding. Light from distant objects has been stretched by this expansion, shifting to redder wavelengths. The amount of stretching, the redshift, depends on how much the universe has expanded since the light was emitted. For distant objects, astronomers often give distances not in parsecs but in terms of redshift. Redshift is a direct observable. It can be measured from spectra. It does not require any assumptions about the distance ladder. But redshift is not a distance. To convert redshift to distance, you need a cosmological model. You need to know how fast the universe is expanding, how that expansion has changed over time, how much matter and dark energy the universe contains. With a model in hand, you can convert. And the distances you get are expressed in megaparsecs or gigaparsecs. This is slightly awkward. The parsec, which originated from parallax measurements of nearby stars, is now labeling distances derived from cosmological models of the expanding universe. The connection to parallax is purely formal. No one is measuring parallax at cosmological scales. And yet the unit persists. It provides continuity with smaller scales. It allows comparisons across the distance ladder. It is the common currency of astronomical distance, regardless of how that distance is measured. Here is something to notice. At very large scales, the concept of distance itself becomes ambiguous. In an expanding universe, there are multiple ways to define distance. The light travel distance is how far the light travelled. The proper distance is the distance as measured at a specific moment. The co-moving distance factors out the expansion, giving a distance that remains constant as the universe expands. These different definitions can give very different numbers for the same object. A galaxy with a redshift of 1 might be about 3 gigaparsecs away by co-moving distance, but only about 5 billion light-years by light travel time. This is confusing. It reflects a genuine ambiguity in what distance means in cosmology. The universe does not have a single, unambiguous notion of distance at large scales. Astronomers navigate this by being explicit about which distance they mean. They specify co-moving distance, or luminosity distance, or angular diameter distance, depending on context. The parsec appears in all of these, scaled up to megaparsecs or gigaparsecs. The unit is consistent, even if the concept it measures is not. This is another case where the unit carries more history than physics. The parsec, born from the simple geometry of parallax, now labels quantities that arise from the complex mathematics of general relativity and cosmological models. The connection is tenuous, but the convention persists. Let us step back and reflect. We have traced the parsec from its origins in 19th century parallax measurements to its use in 21st century cosmology. Along the way, we have seen how it became embedded in astronomical practice, how it resisted replacement, how it scaled up to label distances far beyond its original domain. The parsec is a survivor. It has outlasted the computational constraints that motivated it. It has adapted to technologies its inventors never imagined. It has become part of the infrastructure of modern astronomy, used without thought by thousands of researchers every day. And it will likely continue. Not forever, perhaps. Nothing lasts forever. But for the foreseeable future, the Parsec is here to stay. What does this tell us? It tells us that science is a human activity. It is shaped by history, constrained by practicality, tolerant of imperfection. The Parsec is not optimal, but it is good enough. And good enough in a world of limited time and resources is often enough. It tells us that tools matter. The units we use, the conventions we adopt, the frameworks we think within, all of these shape how we understand the world. The Parsec is not just a label, it is a way of thinking about distance connected to observation and measurement, carrying forward the insights of generations. It tells us that continuity has value. Science advances by building on what came before. The Parsec, by remaining constant, provides a thread connecting past and present, allowing old work to remain accessible, enabling cumulative progress. These are not grand lessons. They are quiet observations about how science actually works. The Parsec, that strange and persistent unit, illuminates them in its modest way. Let us consider how a working astronomer experiences the Parsec in daily practice. It is Monday morning. You are an astronomer at a university and you have data to analyze. You open your laptop and load the latest results from a survey of star-forming regions in the galaxy. The data arrive in standard formats. Stellar positions are given in celestial coordinates. Distances are given in parsecs, derived from Gaia parallaxes. Velocities are given in kilometers per second. You do not think about why the distances are in parsecs. They just are. This is how the data come. This is how the software expects them. This is how your colleagues discuss them. You run your analysis. You make plots. You compare your results to models. Throughout, the Parsec is simply there, a background assumption, never questioned. This is how it is for most astronomers most of the time. The Parsec is not a topic of reflection. It is a tool used automatically, like the keyboard under your fingers or the chair under your back. Only occasionally, perhaps when teaching an introductory class or talking to a journalist, does an astronomer stop to think about what a parsec actually is. And even then the explanation is brief, a digression before returning to the real subject. The parsec works precisely because it is unremarkable. It does its job without drawing attention to itself. This is the highest compliment a unit can receive. Let us think about the future of distance measurement. Parallax, the technique that gave us the parsec, will remain important for the foreseeable future. Gaia has revolutionized the field, but there is more to come. Future missions may achieve even higher precision, extending the reach of parallax to greater distances. Other techniques will continue to develop as well. Standard candles will be refined. Gravitational wave observations may provide new ways to measure distance. The cosmic distance ladder will grow more rungs. Through all of this, the parsec will likely remain. It is too deeply embedded to remove. And there is no pressing reason to remove it. It works. A century from now, astronomers may still be using parsecs. They may think of them as quaint, a historical relic from the early days of stellar distance measurement. But they will use them nonetheless, because the alternative would be pointless disruption. 2 centuries from now, who knows? If humanity has spread beyond Earth, if we have direct experience of interstellar distances, the parsec may finally seem inadequate. A new unit, based on human travel or communication across stellar distances, might emerge. But even then, the historical literature would remain in parsecs. The old papers, the old catalogues, the old databases. A new unit would supplement the parsec, not replace it. The past cannot be rewritten. Let us end where we began, but with a different perspective. You are standing at the edge of a field, looking at a distant tree. You close one eye, then the other. The tree shifts. This is parallax, the foundation of the Parsec. Now you know the story. You know how 19th century astronomers used this simple principle, scaled up to cosmic dimensions, to measure the distances to stars for the first time. You know how the Parsec emerged from that measurement, a unit designed for computational convenience, embedded in the geometry of Earth's orbit. You know how the Parsec persisted long after its original purpose became obsolete, because changing it would be more trouble than it is worth. You know how it scaled up, from parsecs to kiloparsecs, to megaparsecs, to gigaparsecs, labeling distances from the nearest stars to the edge of the observable universe. You know that the Parsec is strange, unintuitive, a historical artifact carried forward by inertia. And you know that this is fine. Science does not require perfection. It requires tools that work. The Parsec works. There is something satisfying in this story. It is not a tale of triumph or discovery. It is a tale of persistence, of continuity, of making do with what you have. The Parsec is not glamorous. It is not exciting. It is just useful. And useful in the end is what matters. The universe is vast. Our tools for understanding it are imperfect. But imperfect tools, used carefully and consistently, can reveal wonders. The Parsec is one such tool. It has done its job for nearly 2 centuries. It will do its job for centuries more. And somewhere right now, an astronomer is writing a paper. The distances in that paper are in parsecs. The astronomer does not think about why. It is just how things are done. This is science. Not a pristine temple of pure reason, but a human activity shaped by history, constrained by practicality, moving forward one careful step at a time. The Parsec is part of that story, a small part perhaps, but a part nonetheless. Let us consider one more thought before we close. The Parsec is a reminder that science is made by people, not by abstract intellects, not by disembodied rationality, but by human beings with limited time, limited resources, limited patience. People make choices. They choose units, conventions, methods. They choose based on what is practical, what is familiar, what works. Not always what is optimal, because optimal is often unknown or unattainable. These choices accumulate. They become traditions. They shape how future generations think and work. The Parsec is one such accumulated choice, a decision made long ago that continues to influence astronomy today. There is nothing wrong with this. It is how all human knowledge develops. We inherit from our predecessors. We build on what they gave us. We pass something on to those who come after. The Parsec will be part of that inheritance. Future astronomers will receive it, use it, perhaps wonder briefly about its origins, and then move on to their own work. And that is as it should be. The Parsec does not need to be celebrated. It does not need to be defended. It just needs to be used. That is its purpose. That is its value. So the next time you hear a distance given in parsecs, you can smile a little. You know the story now. You know why this strange unit persists. You know that it carries within it the history of astronomical measurement, the geometry of Earth's orbit, the practical decisions of long-dead astronomers. The Parsec is a human artifact. It is imperfect, arbitrary, contingent, and it works. That is enough. The stars continue to shine at their various distances. The Parsec continues to label those distances. The universe continues to be vast and strange and wonderful, and we continue to measure it, one parsec at a time. There is nothing more to say about the Parsec itself, but perhaps there is something more to notice. The fact that you can think about parsecs at all is remarkable. 100,000 years ago, Your ancestors looked at the same stars and saw only points of light. They told stories about them, navigated by them, perhaps worshipped them, but they did not know what they were or how far away. Now you know. You know that stars are distant suns. You know how far away they are. You know the unit used to measure that distance, its history, its quirks, its persistence. This is knowledge that did not exist a few centuries ago. It was hard-won, built up through patient observation, clever technique, cumulative effort. The Parsec is a small piece of that edifice, a brick in the wall of understanding. You are heir to this knowledge. Simply by learning about the Parsec, you have connected yourself to a tradition stretching back to Bessel and Henderson and Struve, the astronomers who first measured stellar distances. You stand on their shoulders, seeing further because of what they did. This is the great gift of science. It is cumulative. Each generation adds something. The knowledge grows. And anyone can share in it simply by learning what has been learned. The Parsec is part of what has been learned. Now you know it too. And so the knowledge passes on, from those who discovered to those who learn, from the past to the present to the future. An unbroken chain of understanding stretching across the generations. The Parsec, that strange unit, is a link in that chain. It connects you to the astronomers of the past and to the astronomers yet to come. It is a shared convention, a common language, a piece of the scientific heritage that belongs to everyone. Use it well. Or more likely, simply know that it exists, part of the vast background of human knowledge, quietly doing its job while you go about your life. The stars are far away. The Parsec measures how far. And science continues, one discovery at a time, building understanding, extending reach, illuminating the universe. That is the story of the Parsec. It is not a dramatic story. It is not a triumphant story. It is just a human story about a tool that worked and kept working long after anyone remembered why it was made. There is something peaceful in this. The Parsec does not demand your attention. It does not insist on its importance. It just is. A unit, a convention, a way of talking about distance. And in that quietness, there is something valuable. Not everything needs to be exciting. Not everything needs to be revolutionary. Sometimes, the most important things are the ones that simply work, day after day, without fuss or fanfare. The Parsec is one of those things. It works. It has always worked. It will continue to work. And that, in the end, is what matters. The stars shine. The distances stretch. The Parsec measures. And life goes on. It is a good arrangement. Imperfect, perhaps, but good. And now, knowing all this, you can look at the night sky with a slightly different appreciation. Those points of light are not just pretty dots. They are suns, at distances measured in parsecs, scattered across a vast three-dimensional space. The nearest is about 1.3 parsecs away. The farthest you can see with your naked eye is a few thousand parsecs. Beyond that, galaxies extend to billions of parsecs, to the edge of the observable universe. All of this labelled in a unit invented for the convenience of 19th century calculators. A unit that persists through inertia, through practicality, through the simple fact that it works. The universe does not care about our units, but we need them. They are how we make sense of things, how we communicate, how we build understanding. The Parsec is one of our units. It is strange, it is historical, it is contingent, and it is ours. That is the story. That is the Parsec. Now you know, but perhaps there is more to sit with. Consider for a moment the idea of a convention. We use this word casually, but it points to something interesting. A convention is an agreement, usually unspoken, to do things a certain way. Not because that way is inherently superior, but because agreement itself has value. The parsec is a convention. Astronomers agree to use it. They do not sign contracts or swear oaths. They simply learn it, use it, and pass it on. The agreement is implicit, woven into the fabric of the discipline. This kind of implicit agreement is everywhere in human activity. We agree to drive on one side of the road. We agree on the meanings of words. We agree that certain sounds constitute music and others do not. These agreements are not natural laws. They could have been different. But once established, they persist. The parsec is like this. It could have been different. Astronomers could have chosen the light year or invented something else entirely, but they chose the parsec, and now we all use it. The choice was made long ago by people who did not know they were setting a precedent for centuries. This is worth noticing because it reveals something about how human knowledge is structured. It is not just facts and theories, it is also conventions, practices, habits of thought. These are the scaffolding that supports the edifice of understanding. Without conventions, science would be impossible. Scientists could not communicate. Results could not be compared. Progress could not accumulate. The parsec, humble as it is part of what makes astronomy a coherent discipline rather than a collection of isolated efforts. Let us think about the texture of scientific communication. When an astronomer writes a paper, they do not start from first principles. They assume a shared background. They use standard terminology, standard units, standard methods. The reader is expected to know these things already. This shared background is what allows papers to be short and focused. An astronomer does not need to explain what a parsec is every time they mention one. They can simply write the number and move on. The reader understands. This efficiency comes at a cost. The shared background can become invisible. Astronomers may forget that their conventions are conventions, that their units are historical choices rather than natural necessities. They may assume that their way of thinking is the only way. This is a common pattern in expertise. Experts internalize their conventions so deeply that they cease to notice them. The conventions become like the air they breathe, essential but unexamined. The parsec is part of this invisible background for astronomers. They use it without thinking, without questioning. Only when they step back, perhaps when explaining to an outsider, do they notice how strange it is. This is not a criticism. It is simply how expertise works. You cannot be expert in something and simultaneously maintain a naive perspective on it. The conventions must be internalized to be useful. But it is good occasionally to remember that they are conventions. Let us consider the broader context of measurement in science. Measurement is fundamental to science. It is what distinguishes science from other ways of knowing. Philosophy relies on argument, religion relies on revelation, art relies on expression, science relies on measurement. This reliance on measurement is both strength and limitation. It is a strength because measurements can be checked, repeated, compared. Different scientists, working independently, can verify each other's results. This is what gives science its objectivity, its claim to truth. But it is also a limitation because not everything can be measured. Consciousness, meaning, value, these are not easily quantified. Science struggles with them, not because scientists are incompetent, but because the methods of science are designed for measurable quantities. The parsec is a unit of measurement. It is designed for a quantity that can be measured, distance. Distance is one of the most fundamental measurable quantities. It is what makes space spatial. By measuring distances to stars, astronomers transform the sky from a flat backdrop into a three-dimensional arena. The parsec was part of that transformation. It is a tool for turning angular positions into spatial locations. This is a deep achievement. For most of history, the stars were at unknown distances. They could have been very close or infinitely far. The measurement of stellar parallax resolved this ambiguity. The stars are far, but not infinitely so. They are suns at measurable distances. The parsec is a memorial to this achievement. Every time an astronomer writes a distance in parsecs, they are implicitly celebrating the moment when the universe became measurable. Let us think about the relationship between units and reality. Units do not describe reality directly. They describe our measurements of reality. This is a subtle but important distinction. The stars are at certain distances from us. Those distances exist whether or not we measure them. But the number we assign to a distance depends on our choice of unit. The same distance is 1.3 parsecs, 4.3 light years, or 40 trillion kilometers. The distance is the same. The number changes. This might seem obvious, but it points to something important. Our descriptions of reality are always mediated by our choices. The units we choose, the concepts we use, the frameworks we think within, all of these shape how we understand the world. This does not mean reality is subjective. The distance to Alpha Centauri is what it is, regardless of what we think about it. But our access to that distance, our ability to talk about it and reason about it, depends on the tools we have constructed. The parsec is one such tool. It is a human construction, designed for human purposes. It does not reveal the distance to stars. It provides a way of talking about that distance, a framework for organizing our measurements. Without such frameworks, we could not think about distances at all. The numbers would be meaningless, unconnected to anything. The parsec, by providing a reference point, a scale, makes cosmic distances thinkable. This is what all units do. They provide reference points. They connect quantities to something we can grasp, even if only abstractly. The parsec connects stellar distances to the geometry of Earth's orbit, to the technique of parallax measurement, to the history of 19th century astronomy. These connections are what make the unit meaningful. A number without connections is just a number. A number in parsecs carries its history, its method, its place in the web of astronomical knowledge. Let us consider the experience of looking at the night sky. You go outside on a clear night, away from city lights. The stars are scattered above you, thousands of points of light against the dark. They seem close, as if you could reach up and touch them. But you know better. You know that even the nearest star is unimaginably far. You know that the light reaching your eyes has traveled for years, decades, centuries, depending on which star you look at. This knowledge does not change what you see. The stars still look close. Your brain cannot override its instincts. But the knowledge adds a layer of meaning. You are not just seeing pretty lights. You are seeing the universe, vast and ancient. The parsec is part of this knowledge. It is a way of quantifying the distance, of putting a number on what you instinctively perceive as close. Proxima Centauri, the nearest star, is 1.3 parsecs away. Vega, one of the brightest stars, is about 7.7 parsecs away. Deneb, one of the most luminous stars visible to the naked eye, is perhaps 800 parsecs away. These numbers do not make the distances imaginable. You cannot picture 800 parsecs any more than you can picture 800 million or 800 trillion of anything. But the numbers provide landmarks. They tell you something about the relative distances, about which stars are nearby and which are far. This is the practical value of the parsec. Not to make cosmic distances comprehensible, which is probably impossible, but to make them comparable. You can see at a glance that Deneb is about 100 times farther than Vega. You can reason about these distances, even if you cannot visualize them. And so the parsec serves its purpose. It is a tool for thought, a way of organizing knowledge, a framework for understanding. It is not perfect, it is not elegant, but it works. Let us now think about the oddity of measuring very large things with very small angles. This is the heart of the parsec's strangeness. A parsec is defined in terms of an arcsecond, which is a tiny angle. An arcsecond is 1 to 3600 of a degree. It is the angle subtended by a quarter held at a distance of about 5 kilometers. The parsec, then, is the distance at which this tiny angle corresponds to the radius of Earth's orbit. Work out the geometry, and you get about 31 trillion kilometers. There is something almost vertiginous about this. We start with an angle so small that most people cannot perceive it. We connect it to the size of Earth's orbit, and we end up with a distance so large that light takes years to cross it. The mathematics makes perfect sense. Geometry is geometry. The relationships between angles and distances are well established, but the intuitive leap from tiny angles to vast distances is disorienting. This is characteristic of astronomy. The subject constantly involves extreme ratios, tiny effects that imply enormous conclusions. The slight wobble of a star implies a distance of trillions of kilometers. The faint dimming of a distant sun implies a planet passing in front of it. The tiny shift in a spectrum implies a galaxy rushing away at millions of kilometers per hour. Astronomers are used to this. They work with extreme ratios routinely, but for the rest of us, it takes some adjustment. The parsec is one entry point into this strange world of tiny signals and vast implications. Let us consider what it means to develop intuition for something unintuitive. We have talked about how astronomers develop intuition for parsecs. They learn to associate different numbers with different scales. A few parsecs is nearby. A few thousand is galactic. A few million is cosmological. This is a kind of learned intuition. It is not the intuition you were born with, the intuition that evolved for navigating forests and tracking prey. It is intuition that you develop through practice, through exposure, through repeated use. This kind of learned intuition is common in skilled activities. A musician develops intuition for harmony. A cook develops intuition for flavor. A programmer develops intuition for code. None of these intuitions are innate. They are all built up through experience. The parsec is part of the astronomer's learned intuition. Over years of working with the unit, they develop a feel for what different numbers mean. This feel is not visual. They cannot picture a parsec, but it is cognitive. They know where different distances fit in the scheme of things. This cognitive intuition is what would be lost if astronomers switched units. Not just the numbers, but the associations, the context, the sense of scale. This is why the parsec persists, even though it is unintuitive in the ordinary sense. It has become intuitive for those who use it through years of practice. Let us think about the social nature of scientific conventions. Conventions are inherently social. They only work if people agree to follow them. A convention followed by only one person is not a convention. It is a quirk. The parsec is a social convention. It works because astronomers around the world agree to use it. This agreement is not formal. There is no parsec police enforcing compliance. But there is social pressure. Papers written in non-standard units are harder to read. Results presented in unfamiliar terms are harder to compare. Non-conformity has costs. This social pressure is what maintains conventions. People follow them because everyone else does. And everyone else does because everyone else does. The circle is self-reinforcing. Breaking out of such circles is difficult. Even if a new unit were objectively better, adopting it would mean breaking with convention. You would be the odd one out, using units that no one else uses, making your work harder to integrate with the mainstream. This is why conventions persist even when they are not optimal. The cost of switching is borne by the individual, while the benefits, if any, are shared by everyone. The incentives favor conformity. The Parsec benefits from this dynamic. Even astronomers who privately think the unit is awkward will use it publicly because that is what everyone else does. The convention sustains itself. Let us consider the difference between precision and accuracy. Precision refers to how finely you can measure something. Accuracy refers to how close your measurement is to the true value. They are related but distinct. A measurement can be precise but inaccurate. You might measure a distance to 3 decimal places, but if your instrument is miscalibrated, all your digits are wrong. Conversely, a measurement can be accurate but imprecise. You might know the rough distance to a star plus or minus a factor of 2, which is accurate but not very precise. The parsec is well suited to expressing precision. Because it is defined in terms of arc-seconds, and because parallax measurements naturally produce arc-second values, the precision of a parallax measurement translates directly into the precision of the distance in parsecs. If your parallax measurement has an uncertainty of 0.01 arc-seconds, you can immediately see what that means for the distance. The reciprocal relationship between parallax and distance in parsecs makes error propagation transparent. This transparency is one of the parsec's virtues. It keeps astronomers connected to their data, aware of where the uncertainties are, able to assess the reliability of their results. A different unit might obscure this. If distances were expressed in some other unit, the relationship between parallax uncertainty and distance uncertainty would be less obvious. Astronomers would have to calculate more, think harder, be more susceptible to mistakes. This is a small thing, but small things matter in science. The parsec, by keeping error propagation simple, helps astronomers stay rigorous. Let us think about the history of failed alternatives. Over the years, various alternatives to the parsec have been proposed. Some astronomers have argued for the light year, others have suggested entirely new units. None of these proposals have gained traction. Why not? Partly inertia, as we have discussed, but also because none of the alternatives offered significant advantages. The light year is more intuitive for the public, but not for astronomers doing actual research. New units would have to be learned from scratch, with no established literature to support them. The proposals failed not because they were bad, but because they were not enough better. The parsec works. To replace it, you need something that works significantly better. No such thing has appeared. This is a common pattern in the evolution of standards. Existing standards persist not because they are optimal, but because alternatives are not compelling enough to justify the transition costs. The devil you know is preferable to the devil you do not. The parsec is the devil astronomers know. It has quirks, but they are familiar quirks. Astronomers have learned to work with them. A new unit would have new quirks, unfamiliar ones, and the process of learning them would be painful. So the parsec remains, not because it is beloved, but because it is established. Establishment is a powerful force. Let us consider what the parsec tells us about the nature of scientific progress. Science is often portrayed as a series of breakthroughs. New theories overthrow old ones. New discoveries reveal hidden truths. The march of progress is dramatic and discontinuous. But most science is not like this. Most science is incremental, cumulative, conservative. It builds on what came before. It uses established tools. It follows established conventions. The parsec exemplifies this everyday science. It is not a breakthrough. It is a tool used day after day, enabling the small steps that accumulate into large advances. Without such tools, the breakthroughs would be impossible. This is worth remembering when we think about science. The headlines go to the discoveries, the paradigm shifts, the revolutions. But the real work is done with tools like the parsec, unglamorous and essential. The parsec will never win a Nobel Prize. No one will ever be famous for inventing it. but it has enabled countless discoveries by countless astronomers. It is part of the infrastructure of knowledge. Let us think about the concept of intellectual infrastructure. Infrastructure usually refers to physical things, roads, bridges, power grids. But there is also intellectual infrastructure, the concepts, conventions, and tools that enable thought. The Parsec is part of astronomy's intellectual infrastructure. It is a shared concept, a common language, a standardized tool. Without it, astronomers would have to reinvent ways of talking about distance every time they communicated. Intellectual infrastructure is often invisible. We do not notice it until it fails. The Parsec works so smoothly that astronomers rarely think about it. It is only when you step back and ask why this particular unit exists that you begin to see the infrastructure it provides. All fields have intellectual infrastructure. Mathematics has its notation. Logic has its rules. Music has its theory. These infrastructures are not natural. They are built up over centuries, refined through use, passed down through generations. The Parsec is one element of astronomy's intellectual infrastructure. It is neither the most important element nor the least. It is simply part of the whole, one piece of the apparatus that makes astronomy possible. Let us consider the Parsec in the context of other astronomical conventions. Astronomy is full of conventions that might seem strange to outsiders. Magnitudes, for instance. The brightness of stars is measured in a logarithmic scale where smaller numbers mean brighter stars. A star of magnitude 1 is brighter than a star of magnitude 5. This is counterintuitive, the reverse of what you might expect. Why? Historical reasons. The ancient Greeks ranked stars by brightness, with the brightest being first magnitude and the faintest visible being sixth magnitude. When modern astronomy quantified this system, it inherited the backwards scale, or consider right ascension, one of the coordinates used to locate objects in the sky. It is measured in hours, minutes, and seconds, not degrees. Why? Because the sky appears to rotate once every 24 hours, and it was convenient to connect sky coordinates to time. Or consider the convention of measuring stellar temperatures in Kelvin, a scale where 0 is absolute zero and room temperature is about 295. This is logical from a physics perspective, but it takes some getting used to. The Parsec fits into this context. It is one of many astronomical conventions that reflect the historical development of the field. These conventions are not always logical. They often carry historical baggage. But they work and they provide the shared language that astronomers need. Let us think about the experience of learning astronomy. If you take an astronomy class, you encounter many unfamiliar concepts. You learn about magnitudes and right ascension and parsecs. You learn how distances are measured, how stars are classified, how galaxies are categorized. At first, it all seems arbitrary. Why this system rather than some other? Why these conventions? The answers, when you learn them, often come down to history. This is how things have been done. This is what the field inherited. Over time, if you continue in astronomy, these conventions become familiar. They stop seeming arbitrary and start seeming natural. This is the process of becoming an expert. You internalize the conventions until they feel inevitable. The Parsec is part of this internalization. Students learn it, use it, eventually stop thinking about it. It becomes part of their mental furniture, as natural as the concept of temperature or time. This is how disciplines perpetuate themselves. They train new members in the conventions of the field. The conventions are passed down, generation to generation, maintaining continuity even as knowledge expands. Let us consider the aesthetics of the Parsec. We have talked about whether the Parsec is intuitive or convenient or precise. But what about beauty? Is the Parsec beautiful? This might seem like an odd question. Units are not usually evaluated aesthetically, but scientists do sometimes talk about the beauty of their tools and concepts. A beautiful equation, an elegant proof, a satisfying theory. By these standards, the parsec is not beautiful. It is awkward, historical, contingent. It does not have the elegance of a fundamental constant or the simplicity of a natural unit. But perhaps there is a different kind of beauty here. Not the beauty of elegance, but the beauty of function. The parsec works. It does its job. It has done its job for nearly 2 centuries. There is a craft aesthetic that values things that work well, regardless of whether they are beautiful in a conventional sense. A well-made tool, even an ugly one, can have a kind of beauty in its fitness for purpose. The parsec has this kind of beauty. It is not pretty, but it works. And there is something to appreciate in that. Let us think about the relationship between the parsec and human limitations. The parsec exists because humans have limitations. We cannot travel to the stars. We cannot measure distances directly. We can only observe from Earth, looking at the sky, measuring angles. Parallax is a technique for working around these limitations. It uses the motion of Earth to create a baseline, allowing indirect measurement of what cannot be measured directly. The parsec is a product of this technique. It is optimized for the limitations under which astronomers work. It is not what we would design if we could travel freely through space. It is what we design when we are stuck on one planet looking out. In this sense, the parsec is a testament to human ingenuity. We cannot overcome our limitations, but we can work around them. We cannot go to the stars, but we can measure how far away they are. The parsec is part of this achievement. There is something humbling in this. The parsec reminds us that our knowledge is hard-won, achieved against the constraints of our situation. We are not gods, surveying the universe from above. We are creatures on a small planet, peering out through telescopes, doing the best we can. And our best is pretty good. The parsec, awkward as it is, enables precise measurement of cosmic distances. It works. It is a triumph of human capability, achieved within human limitations. Let us consider what would happen if we discovered interstellar travel. This is speculative, of course. We have no interstellar travel, and we may never have it. But it is interesting to think about how the parsec might change if our relationship to cosmic distances changed. Right now, the parsec is a unit for observation. We look at stars and measure how far they are. We do not go there. The parsec is appropriate for this observational stance. If we could travel to the stars, we might want different units. Units based on travel time, perhaps, or units based on the energy required to reach a destination, or units that feel more grounded in human experience. We already see this in science fiction. Authors often invent new units for interstellar distances, units that make sense for travelers rather than observers. Light years are common because they connect to the speed limit of travel. If interstellar travel became real, the parsec might gradually fade from everyday use. It would remain in the scientific literature, in the historical record. But practical interstellar navigation might use something different. This is speculation, of course. We do not know if interstellar travel will ever happen or what it would look like if it did. But it is a reminder that the parsec is contingent on our situation. It is not eternal. It is a tool for the current era, when we observe but do not travel. Let us think about the parsec in the context of cosmic humility. Astronomy is a humbling discipline. It reveals our smallness. The Earth is a tiny planet around an ordinary star in one galaxy among billions. The distances are vast. The timescales are immense. Humans are recent arrivals on a cosmic timescale. The parsec is part of this humbling context. Every time an astronomer uses the parsec, they are implicitly acknowledging the scale of the universe. The nearest star is more than a parsec away. The galaxy is tens of thousands of parsecs across. The observable universe is billions of parsecs in every direction. These numbers are not meant to make us feel small, they are just measurements. But they have that effect nonetheless. The parsec, by quantifying cosmic distances, makes our smallness precise. This is not cause for despair. Our smallness does not diminish us. We are still conscious beings, capable of wonder, capable of understanding. The very fact that we can measure the universe in parsecs is a kind of triumph. But the humility is appropriate. We are not the center of the universe. We are not its purpose. We are inhabitants, observers, brief sparks of awareness in a vast cosmos. The parsec helps us see this clearly. It is a tool for precision, and precision reveals the scale of things. Let us consider the parsec as a cultural artifact. We have talked about the parsec as a scientific tool, but it is also a cultural artifact, a product of a particular time and place, carrying the marks of its origin. The parsec was invented in Europe in the 19th century during a period of rapid scientific advancement. It reflects the concerns and capabilities of that era, the emphasis on precision measurement, the development of sophisticated instruments, the growing understanding of stellar distances. If astronomy had developed differently, in a different culture or a different era, the unit might have been different. The parsec is not inevitable. It is contingent on the history that produced it. This does not make it less valuable, but it is worth remembering that the parsec is a human creation, not a natural kind. It could have been otherwise. It happened to be this way because of the particular path that history took. All units are like this. All conventions are like this. They are products of history, shaped by circumstance, carrying the marks of their origins. The parsec is no different. Let us think about the persistence of the parsec in the face of technological change. When the parsec was invented, astronomers used telescopes and micrometers. They observed by eye. They calculated by hand. The parsec fit this context perfectly. Now, astronomers use spacecraft and digital detectors. They observe with CCDs. They calculate with computers. The context has changed completely. And yet the parsec remains. The technology has been transformed, but the unit persists. This is remarkable. How many other products of 19th century science are still in daily use? The answer is more than you might think. Much of our mathematical notation dates from the 17th century or earlier. The periodic table was developed in the 19th century. The units of temperature, mass, and length have long histories. Science is conservative in its conventions, even when revolutionary in its ideas. The parsec is one example of this conservatism. It has outlasted multiple technological revolutions, remaining useful even as everything around it has changed. This persistence tells us something about the nature of scientific tools. They do not need to be optimal, they need to be adequate. The parsec is adequate. It works well enough that there is no pressure to change. And so it continues, a 19th century artifact in a 21st century science, doing its job, unbothered by the passage of time. Let us consider the relationship between the parsec and scientific literacy. For the general public, the parsec is unfamiliar. Most people have never heard of it. Those who have often remember it only from Star Wars, where Han Solo infamously claimed the Millennium Falcon made the Kessel Run in less than 12 parsecs, confusing distance with time. This unfamiliarity is a barrier to scientific literacy. To understand astronomy at any depth, you need to know what a parsec is. But the unit is strange enough that it requires explanation, context, history. The light year is more familiar. It is used in popular science writing precisely because it is more accessible. The parsec is reserved for professional contexts where its convenience outweighs its strangeness. This creates a kind of double standard. Astronomers use one unit for their work and another for communication with the public. This is not dishonesty, it is adaptation to audience. But it does create a gap between professional and popular understanding. Bridging this gap is part of science communication. Explaining what a parsec is, why it exists, why astronomers use it, this is a way of sharing the culture of science, not just its results. The parsec in this context is a teaching opportunity. It reveals how science actually works, with its historical contingencies and practical compromises. It is a window into the human side of science, the side that popular accounts often neglect. Let us think about the parsec as part of astronomical tradition. Astronomy is one of the oldest sciences. Humans have been tracking the stars for millennia. The discipline has deep roots, connecting modern astronomers to ancient observers. The parsec is part of this tradition. It connects to parallax, which connects to the geometry of Earth's orbit, which connects to the Copernican revolution, which connects to ancient debates about the structure of the cosmos. When an astronomer uses the parsec, they are participating in this tradition. They are using a tool that carries history, that connects them to predecessors who asked the same questions and faced the same challenges. This sense of tradition is part of what makes a discipline. It is not just a collection of facts and techniques. It is a community extended through time, sharing tools and conventions, building on each other's work. The parsec is one thread in this fabric. It is not the most important thread, but it is part of the whole, connecting present to past, enabling the accumulation that makes science possible. Let us consider the future of the parsec one more time. We have discussed how the parsec might fade if interstellar travel became possible, but what about more near-term changes? In the next few decades, astronomy will continue to advance. New telescopes will come online, new missions will be launched. Our understanding of the cosmos will deepen. Through all of this, the parsec will likely remain. It is too deeply embedded to remove, and there is no compelling reason to remove it. The unit will continue to serve, as it has for nearly 2 centuries. Eventually, perhaps in a century or two, the parsec might begin to seem archaic. Future astronomers might learn it as a historical curiosity, the way we learn about alchemical symbols or phlogiston. But even then, it will persist in the literature, requiring anyone who reads old papers to understand what it means. The parsec's future is tied to the future of parallax measurement. As long as parallax remains important, the parsec will remain relevant, and parallax is likely to remain important for a long time. It is the foundation of the cosmic distance ladder. It is the most direct method for measuring stellar distances. It is not going away, so the parsec is probably safe for another few centuries at least. Not forever, perhaps. Nothing is forever, but for longer than any of us will be around to see. And that is fitting. The parsec is a tool for measuring the long-lasting. It should itself be long-lasting. Let us end with a final thought. The parsec is a small thing as things go. It is just a unit, a label, a convention. It does not make headlines. It does not inspire poetry. It does not change the world. But it is part of how we understand the world. It is one piece of the apparatus that lets us measure the cosmos, ask questions, seek answers. Without such pieces, the whole would not exist. Science is made of many small things, units and conventions and techniques, ideas and arguments and data. Each piece is modest. Together they build something vast. The parsec is one such piece. It has done its part for nearly 200 years. It will do its part for many more. And somewhere, tonight, an astronomer is using it, measuring the distance to a star, adding one more data point to the grand accumulation of knowledge. That is the story of the parsec, a strange unit, a historical accident, a practical tool, part of the great human effort to understand the universe. It is not a dramatic story. It is not an inspiring story. It is just a human story about how we make do with what we have, how we build on what came before, how we pass things on to those who come after. The stars shine at their various distances. The Parsec labels those distances. The work continues. And somewhere, far from here, at distances measured in parsecs, the stars keep shining, indifferent to our measurements, waiting to be understood. That is enough. That is the Parsec. That is science. And now perhaps you can rest with this knowledge. The universe is vast. Our tools are imperfect. But we measure what we can, with what we have. The Parsec is part of that effort. It is a good effort. Imperfect, but good. And the night sky waits, full of stars, each one at its distance, each distance now a number we can know. The Parsec lets us know those numbers. That is its gift. That is its purpose. And that finally is all there is to say, or perhaps not quite all. There is something worth noticing about how we arrived here. We started with a simple principle, parallax, the shift in perspective that you experience when you close one eye and then the other. From this everyday phenomenon, accessible to anyone, we built up to a unit that measures distances across the observable universe. This is characteristic of science. It starts with the familiar and extends to the unfamiliar. It takes what we know and uses it to illuminate what we do not know. The Parsec is a bridge between human experience and cosmic reality. The bridge is imperfect. It does not let us truly comprehend cosmic distances. We cannot feel what a parsec means the way we feel what a meter or a mile means. But the bridge lets us reason, calculate, compare. It lets us do science. This is what tools do. They extend our reach. They let us touch things that would otherwise be beyond us. The Parsec lets us touch, in a sense, the distances to the stars, not physically, but cognitively. We can work with these distances, manipulate them, use them to build understanding. Let us think about the relationship between the Parsec and human creativity. Science is often portrayed as discovery. We discover laws of nature. We discover new phenomena. We uncover what was always there. But there is also creation in science. We create theories. We create models. We create units and conventions and frameworks. The Parsec was created. Someone had to think of it, propose it, advocate for it. The creativity involved is not artistic creativity. It is not self-expression. It is the creativity of problem solving, of finding ways to make things work. The Parsec solved a problem: how to talk about stellar distances conveniently. It was a creative solution. This kind of practical creativity is often undervalued. We celebrate artistic creativity and entrepreneurial creativity, but scientific creativity, the kind that produces tools like the Parsec, is equally important. It is what makes science possible. Let us consider the Parsec in the context of scientific communication. Science is a social activity. Scientists do not work in isolation. They communicate with each other, sharing results, building on each other's work. Without communication, there would be no science, only isolated efforts. Communication requires shared conventions, a common language, agreed upon terms and units. Without these, scientists could not understand each other. The Parsec is part of this shared language. When astronomers write distances in parsecs, they know that other astronomers will understand. The unit facilitates communication. It makes science possible. This might seem obvious. Of course, scientists need shared conventions, but it is worth noticing how much depends on these conventions. Science is not just facts and theories, it is also the infrastructure that lets facts and theories be shared. The parsec is infrastructure. It is part of the communication system that makes astronomy a discipline rather than a collection of isolated projects. Let us think about what it would be like to work without shared conventions. Imagine you're an astronomer in a world where everyone uses different units. One colleague measures distances in light years. Another uses some custom unit based on a local standard. A third uses something else entirely. Every communication would require translation. Every comparison would require conversion. Every collaboration would require negotiating units first. The friction would be enormous. Shared conventions eliminate this friction. When everyone uses parsecs, no translation is needed. Results can be compared directly. Collaboration is seamless. This is the value of convention. Not that any particular convention is optimal, but that having a shared convention is better than not having one. The parsec's value lies partly in being shared, not just in its intrinsic properties. Let us consider the concept of lock-in. Lock-in is a term from economics. It refers to situations where an early choice becomes difficult to change, even if better alternatives exist. Once a technology or convention is established, switching costs create barriers to change. The parsec is locked in. Decades of literature use it. Software assumes it. Intuitions are built around it. Even if a better unit existed, switching would be costly. The field is locked into the parsec. Lock-in is often viewed negatively. It suggests being stuck with something suboptimal. But lock-in also provides stability. It means conventions do not change capriciously. It provides the continuity that makes cumulative progress possible. The parsec's lock-in is both a limitation and a strength. It limits change, but it also provides stability. Whether this is good or bad depends on whether change would be beneficial. In the case of the parsec, it is probably neutral. The unit is not causing problems. Lock-in is just maintaining the status quo. Let us think about the relationship between the parsec and scientific authority. Science claims a kind of authority. It claims to tell us true things about the world. It claims that its methods are reliable, its results trustworthy. This authority rests on many things: rigorous methods, peer review, replication, the track record of past success. But it also rests on the appearance of precision and rigor. The way science presents itself matters. The parsec contributes to this appearance. It is a precise unit. Distances given in parsecs sound exact, scientific, authoritative. They sound like knowledge, not guesswork. This is not just appearance. The parsec really is precise. The distances really are measured carefully. But the presentation matters. The unit conveys authority. This is one reason scientific conventions persist. They are part of the apparatus of authority. Changing them might suggest uncertainty, revision, lack of confidence. Keeping them conveys stability and reliability. The parsec, by remaining constant, contributes to the impression that astronomy is a stable, reliable discipline. This impression is not false. Astronomy is stable and reliable. But the impression matters, and the parsec helps create it. Let us consider the parsec in relation to other ways of knowing. Science is not the only way humans try to understand the world. There is also philosophy, religion, art, personal experience. Each offers its own perspective, its own methods, its own claims to knowledge. The parsec is distinctively scientific. It is a unit of measurement, and measurement is central to science. Philosophy does not measure distances. Religion does not measure distances. Art does not measure distances. By using the parsec, astronomy stakes out its territory. It claims to know something precise about the universe, something that other ways of knowing cannot provide. The parsec is a marker of scientific methodology. This is not a criticism of other ways of knowing. Philosophy, religion, and art have their own contributions to make. But science's contribution is distinctive, and the parsec is part of what makes it distinctive. Let us think about the parsec and the democratization of knowledge. One of the remarkable things about science is that its knowledge is, in principle, available to everyone. You do not need special credentials to learn about parsecs. You do not need to be born into a particular family or join a particular group. The knowledge is public. This is relatively new in human history. For most of history, knowledge was closely guarded. Guilds protected trade secrets. Religions controlled access to sacred texts. Power depended on knowledge, and knowledge was hoarded. Science changed this. The knowledge that scientists produce is published, shared, made available. Anyone with curiosity and effort can learn it. The parsec is part of this public knowledge. It belongs to everyone. You can learn what it is, how it works, why it exists. The knowledge is freely available. This democratization is one of science's great gifts. It expands the circle of understanding. It lets anyone participate, at least in principle, in humanity's collective effort to understand the universe. Let us consider the parsec in the context of human mortality. We will all die. This is the one certainty. And when we die, most of what we know dies with us. Our experiences, our thoughts, our understanding all vanish. But some things survive. The things we write down, the tools we create, the conventions we establish. These can outlast us. They can be passed to future generations. The parsec is one such thing. The astronomers who invented it are long dead. But the unit survives. It continues to be used to facilitate understanding, to enable science. This is a kind of immortality, not personal immortality, but the immortality of contribution. The parsec carries forward something of its creators, their ingenuity, their practical problem-solving, their contribution to human knowledge. All lasting human achievements have this quality. They outlive their creators. They become part of a heritage that transcends individual mortality. The parsec is a modest example, but a genuine one. Let us think about what the parsec might mean to someone far in the future. Imagine an astronomer 1,000 years from now if humans still exist and still do astronomy. What will they think of the parsec? They might see it as we see ancient Egyptian cubits or Babylonian measures. A curiosity from the past, a reminder of how science developed, a link to ancestors who faced the same challenges with cruder tools. Or they might still be using it. 1,000 years is long, but the parsec has already survived 200. Conventions can be very durable. The parsec might persist, a relic from an earlier era. Still functional, still adequate. Either way, the parsec will be part of the historical record. Future historians of science, if such people exist, will know about it. They will understand its origins, its quirks, its persistence. The parsec will be evidence of how we, in our era, understood and measured the cosmos. This is another form of persistence, not just functional persistence, continuing to be used, but historical persistence, continuing to be remembered. The parsec will leave a trace in the record of human knowledge long after it ceases to be used. Let us consider the parsec and the question of optimization. We live in a culture that values optimization. We want the best solution, the most efficient method, the optimal outcome. We believe in improvement, progress, refinement. The parsec is not optimal. It could be improved upon in theory. A better unit might be more intuitive, more elegant, more connected to fundamental physics. But the parsec persists despite not being optimal. This tells us something about the limits of optimization. Not everything can be optimized. Not everything should be optimized. Sometimes good enough is good enough. The costs of optimization can exceed the benefits. Switching to a better unit would have costs. Unless those costs are exceeded by benefits, switching is not worthwhile. The Parsec is good enough that switching costs would likely exceed any benefits. This is a lesson in pragmatism. Perfection is not always the goal. Sometimes adequacy is the goal. The Parsec is adequate. That is enough. Let us think about the Parsec and human ambition. Humans are ambitious creatures. We want to understand everything, reach everywhere, accomplish everything. We build towers and rockets and telescopes, reaching ever further, ever higher. The Parsec is a product of this ambition. It exists because we wanted to measure the distances to the stars. Not because we had to, but because we wanted to know. Curiosity drove us. Ambition pushed us. And we succeeded. We measured those distances. The Parsec is the unit we use to express our success. It is a monument to human ambition, a reminder that we have reached further than our ancestors could have imagined. The stars are no longer mysterious points of light. They are suns, at known distances, comprehensible objects in a comprehensible universe. The Parsec helped make them comprehensible. This is the power of human ambition. It pushes us to attempt things that seem impossible, and sometimes we succeed. The Parsec is evidence of one such success. Let us consider the Parsec and the nature of explanation. We have spent a long time explaining the Parsec. What have we actually done? We have traced its history. We have described its definition. We have explained why it persists. We have explored its context, its implications, its oddities. But have we explained why the Parsec is the way it is? In some sense, yes. It is the way it is because of the history that produced it. But history itself is contingent. Things could have been different. Explanation in science is often like this. We explain how things are. We describe the mechanisms, the causes, the history. But the ultimate why, the reason things are this way rather than some other way, often comes down to contingency. Things are this way because they happen to develop this way. The Parsec is contingent. It did not have to exist. It exists because of particular choices made by particular people in particular circumstances. A full explanation includes this contingency. This is not a deficiency of explanation. It is the nature of historical phenomena. The Parsec is a historical phenomenon. Its explanation is historical, and history is contingent. Let us think about the Parsec and the concept of naturalness. We spoke earlier about whether the Parsec is natural. It is not natural in the sense of being demanded by physics. It is not based on a fundamental constant. It is based on the geometry of Earth's orbit, which is accidental. But perhaps naturalness is overrated. What matters is not whether something is natural, but whether it works. The Parsec works. Its artificiality does not prevent it from being useful. Many useful things are artificial. Language is artificial. Mathematics is artificial. Money is artificial. These are human creations, not natural phenomena, but they are essential to human life. The Parsec is similarly artificial and similarly useful. It is a human creation that serves human purposes. Its artificiality is not a flaw. It is simply what it is. Let us consider the Parsec and the experience of doing science. We have talked a lot about the Parsec from an external perspective. What it is, why it exists, how it functions. But what is it like to use the Parsec? What is the internal experience? For most astronomers, the experience is transparent. They use the Parsec without thinking about it. It is part of the background, not the focus. They think about stars and galaxies, not about units. This transparency is the mark of a good tool. A good tool disappears in use. You do not think about the hammer when you are driving a nail. You think about the nail. Similarly, You do not think about the parsec when you are analyzing stellar distances. You think about the distances. The parsec achieves this transparency. It does its job invisibly. This is not glamorous, but it is the highest compliment a tool can receive. Let us think about the parsec and the cumulative nature of knowledge. We have mentioned this before, but it is worth dwelling on. Science is cumulative. Each generation builds on the previous. The knowledge grows. The parsec is part of this accumulation. It was invented by one generation and inherited by successive ones. Each generation uses it, relies on it, builds on it. The parsec is not just a unit. It is a link in a chain of knowledge. This cumulative nature is what makes science powerful. Individual scientists are fallible. They make mistakes. They hold wrong beliefs. But over time, errors are corrected, mistakes are fixed, wrong beliefs are revised. The cumulative process converges on truth. The parsec has been part of this process for nearly 2 centuries. It has supported countless measurements, countless discoveries, countless advances. It is part of the infrastructure that makes accumulation possible. Let us consider the parsec and scientific realism. Scientific realism is the view that scientific theories describe real things. The entities postulated by science, like electrons and quarks and stars, really exist. They are not just useful fictions. Where does the parsec fit in this picture? Is the parsec real? In one sense, no. The parsec is a human invention. It does not exist in nature. You will not find parsecs lying around like rocks or trees. But in another sense, the distances that parsecs measure are real. The distance from Earth to Alpha Centauri is real. It exists whether or not we measure it. The parsec is just a way of expressing that real distance. This is the nature of units. They are not real in themselves. They are ways of talking about real things. The parsec is real in the sense that it refers to real distances. It is not real in the sense of existing independently of human convention. This is a subtle distinction, but it matters. The parsec is conventional, but the distances it measures are not. The conventions are human. The reality is not. Let us think about the parsec and the limits of human knowledge. Human knowledge has limits. There are things we do not know, things we cannot know, things that are beyond our capacity to understand. The parsec does not overcome these limits. It does not let us know everything about the stars. It only lets us know their distances, and even those only approximately, only within measurement error. But the parsec does push back the limits a little. Before parallax measurement, we did not know stellar distances at all. Now we do. The limit has been moved. This is how knowledge advances. Not by eliminating limits, but by pushing them back. The parsec is part of this pushing. It extends our reach even if it does not extend it to infinity. Let us consider the parsec and the emotion of understanding. Understanding is an emotional experience. When you finally grasp something that was puzzling you, there is a feeling of satisfaction, of relief, of pleasure. Understanding feels good. The parsec can be part of this experience. When you first learn what a parsec is, why it exists, how it works, there is a moment of understanding. The confusion clears. The pieces fit together. You get it. This is one of the rewards of learning. The emotional payoff of understanding. The parsec, modest as it is, can provide this reward. It is a small example of the pleasure of knowledge. Let us think about the parsec and scientific literacy. We mentioned scientific literacy earlier, but it is worth returning to. Scientific literacy is the ability to understand and engage with scientific information. It is increasingly important in a world shaped by science and technology. The parsec is a test of scientific literacy, in a way. It requires explanation. It is not self-evident. Understanding it means understanding something about how science works, about parallax, about astronomical measurement, about the persistence of convention. By learning about the parsec, you have become slightly more scientifically literate. You know something about astronomy that many people do not know. This is a small step, but it is a step. Scientific literacy is cumulative. Each small step adds to the previous ones. The parsec is one such step. It adds to your store of understanding, your ability to engage with scientific information. Let us consider the parsec and the idea of perspective. The parsec gives us a perspective on cosmic distances. It is a way of seeing, a framework for organizing our understanding. Different units give different perspectives. Light years emphasize light travel time. Kilometers emphasize sheer magnitude. Parsecs emphasize the geometry of measurement. Each perspective reveals something and hides something else. The parsec reveals the connection to parallax, but hides the connection to light travel time. Light years do the reverse. Neither perspective is complete. This is true of all perspectives. They are partial. They highlight some aspects and obscure others. Understanding involves moving between perspectives, seeing from multiple angles, combining partial views into something closer to a whole. The parsec is one perspective among many. It is valuable, but it is not exhaustive. Full understanding requires more than any single perspective can provide. Let us think about the parsec and the texture of scientific practice. We have talked about science in general terms, but science is not just general principles, it is also specific practices, the day-to-day work of measuring, calculating, checking, revising. The parsec is part of this day-to-day practice. It appears in spreadsheets and databases. It is the output of analysis software. It is the input to models and simulations. It is woven into the texture of astronomical work. This texture matters. Science is not just ideas, it is also practices. The ideas are expressed through the practices. The practices shape the ideas. The two are inseparable. The parsec is part of this texture. By understanding it, you understand something about how astronomy is actually done, not just what astronomers know, but how they work. Let us consider the parsec and the experience of wonder. Science can inspire wonder. The vastness of the cosmos, the intricacy of nature, the power of human understanding, all of these can evoke awe and amazement. The parsec can be part of this wonder, not because it is inherently wondrous, but because it points to wondrous things. The distances it measures are immense. The stars it refers to are astounding. The achievement of measuring them is remarkable. Wonder is not the same as understanding. You can wonder at something without understanding it, but understanding can deepen wonder. Knowing how immense the distances are, knowing how they were measured, knowing what it took to achieve that measurement, all of this can make the wonder richer. The parsec, by helping us understand, can help us wonder. It is a tool for knowledge, but also indirectly a tool for awe. Let us think about the parsec and the passage of time. We have talked about the parsec persisting through time. But what about the time it measures? A parsec is about 3.26 light years. Light from a star, 1 parsec away, takes 3.26 years to reach us. We see that star as it was 3.26 years ago. This is implicit in every measurement in parsecs. Every distance is also a time delay. Every star we see is seen in the past. The farther, the more past. At large distances, this becomes significant. A star 1,000 parsecs away is seen as it was about 3,260 years ago. When that light left, Earth was in the early Iron Age. A galaxy 1,000,000 parsecs away is seen as it was 3.926 million years ago. When that light left, our ancestors were just beginning to walk upright. The parsec, by measuring distance, also measures time. It connects spatial separation to temporal separation. Every measurement is a look into the past. This is built into the structure of astronomy. We cannot see the universe as it is now. We can only see the universe as it was. The parsec labels these distances into the past. Let us consider the parsec and the idea of scale. Scale is one of the fundamental concepts in science. Things happen at different scales. Atoms are small, stars are large, galaxies are larger, the universe is largest. The parsec is suited to a particular scale. It is the right size for stellar distances, for galactic structures. It is too big for planetary systems, too small for cosmology, but just right for its domain. This is how units work. They are suited to particular scales. You would not measure your height in parsecs or the distance to a quasar in millimeters. Different scales call for different units. The parsec occupies its niche. It is the unit for the scale of stars and galaxies. It fits that scale well. This fit is part of why it persists. Let us think about the parsec and the concept of precision. We have talked about precision before, but it is worth emphasizing. Precision is central to science. Vague claims are not scientific claims. Precise measurements are. The parsec enables precision. It provides a unit in which distances can be expressed exactly. Not just that a star is far, but that it is 12.5 parsecs away. Not just that a galaxy is distant, but that it is 780 kiloparsecs away. This precision is what makes science powerful. It allows testing. A theory that predicts a distance of 15 parsecs can be checked against a measurement of 12.5 parsecs. The disagreement is meaningful because the numbers are precise. The parsec is part of the apparatus of precision. It enables the exactness that makes science science. Let us consider the parsec and human curiosity. Curiosity is what drives science, the desire to know, to understand, to figure things out. Without curiosity, there would be no science. The parsec is a product of curiosity. It exists because people wanted to know how far away the stars are, not for any practical purpose, not because it was useful, but because they wanted to know. This curiosity is remarkable. The distances to the stars have no practical relevance to human life. Knowing them does not help you grow crops or build bridges or cure diseases. But people wanted to know anyway. Curiosity for its own sake is one of humanity's finest traits. The parsec is evidence of this curiosity. It is a monument to the human desire to understand, regardless of practical benefit. Let us think about the parsec one last time. We have explored this unit from many angles: its history, its definition, its persistence, its context, its implications, its oddities. We have thought about what it means, why it exists, what it tells us about science. What remains to be said? Perhaps just this: the parsec is human. It is a human creation for human purposes, carrying human history. It is imperfect, contingent, arbitrary, and it works. This is what we do. We create imperfect tools. We use them as best we can. We pass them on to those who come after. The tools evolve, improve, sometimes persist beyond their original purpose. This is the human way. The parsec is part of this. It is not special. It is not exceptional. It is just one example of how we make do, how we build on what we have, how we extend our reach despite our limitations. And through all of this, the stars continue to shine at their various distances. The universe continues to exist, vast and indifferent to our measurements. We are small creatures on a small planet, trying to understand something immense. The parsec helps us understand, not completely, not perfectly, but a little. A tool for reaching further, for knowing more, for extending our grasp. That is what it is. That is what it does. That is enough. The night is full of stars. Each one is at a distance. Each distance can be measured. Each measurement can be expressed in parsecs. And somewhere, an astronomer is doing just that, measuring distances, using parsecs, extending knowledge. The work continues, the parsec serves, the universe waits, and you, having thought about all of this, can rest now. The parsec is explained, the story is told. Understanding has been reached, at least for this small thing. That is the nature of knowledge. It comes in small pieces. Each piece adds to the whole. The parsec is one piece. Now you have it. The stars shine. The distances stretch. The parsec measures. And understanding grows, one small piece at a time.